So this one was just test flight for the first stage. I think it was something about 30 or 40 kilometers height. Of course, the next one will be for 500 kilometers department. So we're very good for launching any kind of payloads. We consider that we can launch payloads from the airspace, from Zona, from orbital, from universities, from Cimatec, from University of Santa Catarina, Maranhão, and everyone who needs, please contact us. We have some cheap launches here in Brazil, in South America, from Alcântara. Oops. It's the beginning. That's the same movie. Okay, thank you. Thank you very much.
Comments, questions, if any questions specific, then you can come back about 6 minutes or we to the next step. Someone wants to make. I just want them to make an announcement. We are working with one group that is developing a Brazilian launcher called MLER, micro launcher, the Brazilian micro launcher. It's headed by Sendic, this group. There are 2 groups. And they allow me to announce that there will be 2 test flights in 17 in 23 months. This is in the proposal, is in the contract. So this will be available for the community, probably very cheap price. They wanted to do operations, to use these flights to do operations with universities. They asked me to do this announcement here. Well, if anyone has other comments or questions about what we have seen, it's the time. We have still 5 minutes. Anyone?
Thanks for the presentation. Everybody, it was very interesting. Thank you very much. I have a curiosity from Wesley. I wasn't aware of the prices in space is actually doing. And you are already telling that price in space is already using that price, or is just a reference?
That's a price of reference. Of course, we are aiming to do that, but for the first launches, as a maiden flight, we are not considering that the prices. We're making that cheaper or difficult services.
My question is to work off. It's regarding the solar panels on the 3 new satellites. Those deployable solar panels. Do you have this technology?
Okay, yes, we integrate, we design and make for right, but we the structure we purchase, but all the design, the order, and the integration we buy our.
But if we place an order to buy the deployable solar panels, we just buy it from you and we'll do all the process. We will import it.
Exactly. We do the deployment, we manufacture, deploy, we integrate all these and make the environmental tests also.
I have another to ADB. Understand. Understand, last week was announced the first couple of payloads for the first orbital flight of space, right? Maybe you want to comment something about this, Wesley or someone from ADB. I understand this flight will happen in March or April next year, right?
Actually, we have meetings with collaboration agreements with states to launch presidents results in this fight. That we remember the results. The first one is it's a satellite done by developed by this Secretary of Federal Education. The partnership with from the top. The second one, it will be supplies from I don't know what the stuff. From the site, it's another satellite. So which starts from India, not all. And the third one, I believe it's the Aldebaran. It's another group starts from the federal part of this of the.
But it's not what they want. It's not what they want. It's another one.
So, both of them. What other information you need from so this is not this is only a package between the space agency.
I think there is another one, maybe.
It's a payload. There is another there is a third one, but it's not. Yeah.
There's a payload. It's a relational system. Also, this one is funded by the space station, which you see. The payload is it's a microelectrical mechanical inertial system developed by Horizon, Concert, and Systems. So it's also a critical system. So inertial systems are critical for launch vehicles, and usually we cannot buy it from other countries due to its too low characteristics. So you can use it in a rocket launch vehicle or maybe in a missile. So the agency is working and it's trying to develop big systems, complete systems, and also subsystems related to the incremental development of launch vehicles and also suppliers. And we want to do more. We are limited by our budgets, but our capacity, we can guarantee that we have the capacity for developing all subsystems and the complete systems. And for launch vehicles and our space.
Thank you very much. There is another.
In space question. How work the insurance in case the launch does not go well and the cargo is lost?
It's mandatory for us by space agency and also from Brazilian Air Force. We have insurance for the vehicle not to harm third parties, but we are not. It's not demanded. It's not mandatory that we have some insurance for the payloads. Of course, if the payload owner needs some insurance, we have some companies, some providers for that. We can give you the contacts, but the launcher by itself doesn't have the insurance for the payload. People usually say that the insurance for the payload from the launch part. But if you need, of course, we have lots of partners of insurance, and we can make the bridge of the payload owner and the insurance company.
Do you know more or less the number of this? If, I mean, 1 kilogram is more or less 20 $20, right? More or less 1 kilogram of launch in the slide. 28 K dollars, right? And the insurance, how the price in comparison.
We are still talking about the payloads. It will depend both of the rocket and the payloads. So the price will differ. For example, it's a CubeSat, university or then called CubeSat, or it's a commercial CubeSat with a very high price. And also, it is an experiment, an instrument like an commercial navigation system. It will differ. So for it, and also it depends on the company. So if it's a Brazilian company, we will price. If it's an English company or a American company, so the prices have a high range of prices. And I'll give
I have a Brazilian company.
yeah. They're not the own providers, they are brokers. So they are intermediates with companies all over the world that provides this insurance for launch services.
I don't know idea more or less in operation with the kilogram launch price.
I cannot give you
It's the same as the dose, the health.
no, I have no idea. We've been talking to them for 1 month or 2 months, but we didn't reach this kind of negotiation yet.
Actually, I think it's not only a matter of addressing the price of the launch, but also the price of the satellite.
Yes.
So that's why it's not able to place it. It depends on how much your satellite costs. So you think the satellite costs 1,000 reais or 1 million reais. So it depends on the price of the satellite.
The proportion, the dogs.
They, for the cube government, it's a small percentage of the price. I would say, so it depends on the rock, but it can vary from 1 to 5%. Something like that.
And of course, you have many types of insurance. You can cover the whole price of the payload, or you can cover just half of the, or just like 30%, which is your operational costs. There are many types of insurance for the same payload, for the same distance.
I have a question for Luciano. You have this in South Beach, you have this high resolution camera. Do you have hyperspectral imaging on the road?
No, actually, this first camera that will be embedded in this satellite, it's done by Opto in São Carlos, and it has 6 spectral bands. So we have red, green, blue, infrared, blue, coastal blue, and red edge, and also a chromatic one. So we have the chromatic, we can achieve 75 centimeters, and all the mode spectral, they are 3 meters. So we make the fusion of them, and the sharpener, sorry. We make the sharpening process, and then we get the 6th band, the spectral band image with 75 centimeters, but it's not the hyperspectral one. It's only one spectrum, 6 bands.
Yeah, I think we finish this panel then, and we thank you all for the participation, and then we'll go to the next section. Thank you very much.
Questo di mesh faccio prima che mi faccio in modo it's not important.
Connect. And the speaker is Luis Angel Fernandez Ramos from Illinois. And the title of the paper is Analysis of the Evaluation of Electron Beam Magnetic Mirror for Possible Plasma Transfer Applications. So let's start doing this. Okay. Very interesting. Any questions? No. Yeah, okay.
So, I remind you, I saw that you're focusing on the election acceleration. Do you plan to extend this automatic model to analyze how the ions can escape them and that model also? We lost the connection.
Well, okay. I was thinking actually ask the same thing because you're talking about an electron beam, but I say what about the ions? Because you generally accelerate ions are really fast. The electrons, so you know, so fast.
Yeah, that's very important.
Yeah, exactly. So I was trying to understand what happened to the ions, because that's what you want to know generally. So, but it looks like we'll never know.
I think we can.
The other questions as well.
No, it was in the same, it was like what was it?
We have the connection.
No, we lost him, yeah. But we have the cross break at 5 minutes. And I think we can go to the cross break and come back.
We break the session and then we continue with in-person presentations, people from the university. Very welcome.
Just one announcement, the coffee break, yesterday it was next the food trucks, right? And today it's in the foyer. So everybody knows where it is. It's just yeah, just yeah, where the reception desk is, just outside
In the front of the auditorium.
the auditorium, yes.
It's when we
The
look,
poster session, yeah.
where we do cocktail.
Yes, then we have it. So let's come back in 20 minutes. What the classes? Okay.
I'm 15.
It's about
to fix one pin of a pocket chip also, but with less time, with less trust and less time of operation. Because you're going to have a more smaller design to fit in the standard.
So right now you guys are already feeling the whole system, the gas, everything in just one half of one unit.
No, not already feeling. The design we're going to later of the final, later September of this next year that we are hoping to achieve that embedded circuit and test and do a live test in a vacuum environment.
And what's the average weight of the system?
For all trusted that we're going to present here are about 1 to 1.5 kilograms, so that's why it's 6 kilograms. But this one specifically, we can reduce it greatly. So about a couple hundred, the whole system.
That's it.
Thank you.
Okay, question. What's the specific impulse of our system and how long can you keep the system in continuous operation?
This kind of boosted plasma trusted, since we are focusing on fixed sets, the specific impulse we are aiming to achieve around 600 seconds. And the time of operation, the trusted itself is going to last much longer than propellant if the satellite can take. So the time, the period of operation will depend on the mass of the propellant that we're going to invest in this solution.
You didn't respond to the question. How long can you keep the system operating?
Oh, so that's really the limit. It's not the electronic circuit or the degradation of the electrodes or the thruster itself. The limiter here is the amount of propellant gas that you can bring with it. So if this kind of thruster, we believe we can operate for a couple thousand hours, but it's posted cycles and doesn't work 24 hours a day because we have to wait for the satellites to charge again the batteries, so you have a more powerful operation. But since the propellant budgets that you can put in the capacity is small, the critical factor here is the amount of propellant and not the ablation of the thruster.
Do you have a series of heat transfer problems and strokes?
Well, with some important talks about the people that work at SET, that's the Unity sites, they had a little problem with temperature, but in the cold side of it. And so it was one solution that was hidden because most sites are predicting the cold side of the curve of the sites, the polymer sites. It's a little heat generated, and so we are moving that heat to the batteries so we can, instead of having some kind of system to heat up the batteries to maintain the optimal temperature, we will use our thruster to heat up other systems.
Okay, let's go to the next paper. Thank you. Next paper. Jonathan is presenting development of radio frequency cathode for cold thrusters.
Hello, everyone. Can you all hear me? Okay.
I thank you all for being here today. My name is John Boboigan. I'm pursuing aerospace engineering at the University of Brasilia, UNB. And this is my junior year there. So today, I'm going to present a little bit of my work, which is my undergraduate thesis on the which was done in collaboration with my peer, Mr. Hudson Costa, and advisors, Professor Rodrigo Miranda and Professor José Ferreira. So today, I'm going to present a little bit of my research here, which is the development of a radio frequency catheter as an alternative for hollow catheters. I don't know if it's not. Okay. So when we're talking about aerospace propulsion systems, it's really important that we rely on the technology that we're getting in space. So this work here, I would like to show you guys that we've been working on the fast ignition of the prototype, which is a difference of hollow catheters. It enhances the lifespan when exposed to the atmosphere, which we can reduce some risks that we have in the laboratory. Reduce the maintenance as well. Simple manufacturing, greater applicability. So this work covers the overall development of the radio frequency catheter and the testing provided on some simulations and tested inside a vacuum chamber as well. Here you can see a 3D model that was designed in SolidWorks. So you can see the picture here showing all parts of the catheter, the whole thing assembled. And the different colors here is related to the materials that was applied to the catheter itself. So some key points here that I would like to stand out is about the ceramics that we have chosen here. It was chosen because of its resistance to stress and temperature, and because of its low cost. This ceramics here is pretty close to what you know as glass, for example, the material properties. So here about the steel we have chosen here is a stainless steel, 316L, maybe know that. This was because of its low cost and availability at the level of the moment that we were doing. Yes, it's here is another thing really important because we were thinking at the beginning to sure that we could use rings made out of rubber, but because of the temperature, we couldn't withstand that kind of part. So we have to work with gaskets made out of rubber. That was due to the resistance to temperature that we're going to see on the next slide. Our content here made out of aluminum wire. The performance, it was chosen because of the performance, low cost, and availability of the as well. Here you can see some simulations that was provided on ANSYS, software ANSYS. You can see the same design that we have here displayed. The simulation conducted. Here you can see the scale of the temperature, the scale of press Celsius and degrees. So you can see the whole thing assembled, which was simulated. You can pay attention that the region in the middle of the ionization chamber, plasma chamber, this is a critical part because we generate the plasma inside of this chamber. And, some key points that I would stand out here is about the temperature, the maximum temperature, which was achieved inside of the chamber. It's good because we don't want something with high conductivity and expanding all the temperature around the device and what is attached to it. So the minimum temperature was achieved outside the chamber, about 300 degrees Celsius. You can see it was pretty much at the screws and some metal parts around it. The ceramics, as I said, it was chosen because of its low conductivity as well. And the RF antenna here was thought about because we were really regarding that matter, and we wanted to take care of not losing the properties of the antenna itself. So on this slide, you can see some simulations provided on console. So from the software. Here, we have conducted some simulations. So the first image is showing a little bit about the electron density of the ground itself. You can see here at the center of the chamber of part kind of red because it is the electron which is confined at the center of the chamber. And close to the walls inside of the chamber, you're gonna see ions close to the walls. These ions are close to the walls because we have an electrode inside of the chamber, the ionization chamber, which is charged with negative potential to attract the ions and confine the electrons at the center of the chamber. So the next figure here, sorry. So the next figure here is about the electron potential. You can see the distribution here, the maximum distribution is in the middle of the chamber as expected because we want these electrons coming out of the chamber later on. And, the lower part value is closer to the lowest, as was mentioned before. So the next image here is showing a little bit about the magnetic flux density, which is pretty cool, image, because we have to ensure that later on we're gonna have to show this because we don't want any problems with satellite or an imply this application. So on the next slide here, you can see the hypothesis of how it works. As I said, it's based on plasma. This is a definition, just for the sake of explanation here. At the left-hand side, you can see here the device itself with illustration, just for the sake of illustration. And some primary connections showing each part of the cathode itself. The main one here is the accelerated electron beams, as you can see here, and I told you about on the previous slide. At the right-hand side, you can see the whole thing assembled inside the vacuum chamber, and the device that we're the secondary devices that we're going to use to make it work. So finally, we have the full semi-assembled cathode. You can see that this is the device that was manufactured with all parts integrated here. Something that I would like to stand out here is about the ion collector, but I have not told you about. So here you can see this connection right here coming out from the side of the chamber itself. This being enabled wire. Which is connected to the ion collector, just this part. And you can see the RF antenna with its connector, assembly connector, just close to around the plasma chamber. So this is the first test that was conducted. It was conducted on the vacuum chamber that we have used. So we wanted to make sure that the antenna was working well, just by itself, right? Some parameters that was set here. You can see this image, just the different angles. There is some physics here, and I explain what is happening here. The adaptation of the antenna here to the system that we had available was very important because we had to make some changes to make it work. But it was for the sake of what happened to our laboratory, which flooding at the beginning of the year, we had then the first flooding laboratory and we lost some equipment. The operating range that was it's a common operating range for this kind of test here of 13.56 megahertz. The applied power, which was 60 watts, it's not because it works with it works less power than that. But as I said, it was adapted to the system that we have. The operating pressure was between 10 to the power of -2 and 10 to the power of -5. Here you can see the whole thing assembled, the antenna around the cathode chamber, and some parts that are a little bit. So this great image is showing a little bit of each part of interest of the problem. So some key points that I would like to send out on the first image is the formation of the plasma inside of the vacuum chamber. You can see this here, right? So the concentration of electrons at the front of the chamber, right here, this part. And I would like to stand out this to know how that is. It looks really pretty much the same thing. Image, I would say. So why is this electron beam coming out of the chamber? Because we have an electrode right here, which is charged with a positive potential to make sure that we're going to have the electron coming out of the chamber. On the next slide, we have some results regarding the temperature simulation that was conducted, as I said, on ANSYS software. The first image is just a little bit about the properties that we started inside of the software itself. And this graph right here is showing temperature versus time of the cathode until it reached the maximum pile of temperature. It was a transient third analysis that was conducted inside ANSYS, and a constant pressure, a constant temperature profile at about 2,000 seconds or 33 minutes. Let's see. Here we have some results regarding the electron extraction, which is the most important part here. We're talking about it because that's what we want. So the first table here is showing a little bit about the mass flow range, ranging from 1 to 6 ccm. A ccm is a unit that we use to measure this kind of things. The maximum current here was a little bit low. But as I said, it was the first test that we conducted, right? And we're working. And at a 4 system, and the minimum current drawn was 0.087 amperes, 5 SCM. Here we have just a plot of the table, just for the sake of illustration here, and we're still trying to figure out what is this formation here close to something in the literature itself. Some final thoughts here that I would like to end out is about the cheap manufacturing regarding all methods. All methods are pretty expensive, and we have to import them, for example, to our country to make sure that we can test, for example, a Hall thruster as a thing. So future application in Hall thrusters, I would like to say that we have to make some adaptations to make sure that we can do that. But it's working right now with our propulsion system that we have in our lab as well. These integration with ion propulsion systems, it doesn't have to be just with the Hall thruster. Any kind of ion propulsion system we can work with. The temperature agreement with the materials used, as we expected, and we have seen on the simulations. The maximum electron cost, as I have mentioned before, was as expected, something pretty well like that. But we're aiming to get at least 1 ampere in future applications. So, future implementation of certain bigger thermal conductivity. We were thinking about the concentration of the temperature inside of the chamber. It could cause some problems in the future. And we already conducted actually a thermal analysis of another material that another professor of ours have given a clue of. And it's a little bit expensive. It's 10 times expensive, but the distribution, because of high conductivity, is better, and it's gonna lower the temperature in 100 degrees Celsius. Some recommendations that I would say talk about here on this work that I have seen when I was conducting the experimentations is the improvement of the system. As I said, we were working with documentation at the moment. It was a target at the electrode outside of the chamber. We were applying 33 volts, but we're aiming to apply 100 volts. Yeah, and I would like to thank all the people that have worked with me on this work for sure, peers here and some others. For further questions, you may ask them right now, or you could just reach me at this email here, Jonathan William Rock, at email. I know that's, I guess you can see here, right? That's it. Thank you very much, and I open up for questions right now.
Jonathan, any questions from the audience?
Oh, you come first. Make a question.
I was already saying, so I already asked lots of questions. No, I've got some observations. You are presenting these to an audience that is not specialized in EP, not an IBC here. So it would be better if you presented, because you said, yes, we're doing these because it can be better than normal hollow cathodes, but you probably should explain what is a hollow cathode and why we use hollow cathode instead of using solid cathode. So you probably should have compared like normal solid cathode, a traditional hollow cathode, there are several types of hollow cathode, and this radio frequency to illustrate to an audience that doesn't work with this every day. Both have the advantages, like, you want to extract like a high current density with a good lifetime. So use cathodes. Cathodes have problems. So radio frequency cathodes can, try to solve some of these problems. So maybe it would have been better to put it more in context. Okay, that's a problem when you present something, you don't go to a specialist conference. So there are people from all sorts of aerospace applications here. Do satellites that do propulsion, people do electric propulsion. So it's like, you're presenting something very, very specialized to an audience that probably doesn't work in with that, apart from me here and you guys. So, should put more in context this thing, I guess. Make it more interesting for the people. I guess. Anyone else?
What's the difference between an inrush current that you use to operate your system with the operational current?
Didn't get the question. What's the difference with
the value of the inrush current that you use to turn on your system with the operational current that you can use to keep your system operating?
What's the first question that you were talking about?
Inrush current. When you turn on, the current achieves a spike.
Okay, so the difference here, as I have most of it in the class here, it is that it's 3 volt current with your cathode, and we were comparing. Let me see. We were comparing this right here with the current words that we have. For example, some words. Excuse me. Oh, no. It's not.
This the same.
Sorry. So the difference here is it's pretty close to other systems that we have seen when we're developing this technology, but this, for example, this values here was a little bit higher than expected because you can see the dimensions here, but I can't talk about it. It's pretty low. You can see that the diameter of the device is 30 millimeters, and the length of the device is this plant meters. So it's centimeters, sorry. So it's just because of the size of the device itself, we would run a lower current compared with the currents that we have recording. I don't know if you can answer the question.
It's okay.
Okay.
Okay, I think the volumes were pretty late, so if you have questions for example, you can, ask him during lunch or something like that. Okay, thank you very much. John. Okay, next speaker is by William Sinesio, as competitive study of propellant injection modes in a low power helium thruster.
Look, it's usually,
Right?
it's usually not million.
Oh, it's switched here, so yeah,
No, but what's it?
yeah, but the notebook,
The only.
well, sorry.
And that's the next.
Yeah.
Yes, that's the next.
So it really was be swapped here on the vanilla application. Happens. So Julio said something I will later.
Today I'm going to talk about our intensive study of propellant injection modes and low power and plasma thrust. This work is divided in an introduction, objective, low power and plasma thrust, methodology, results, conclusion, and review. With external power space and electrical engineer, we had the crazy having size of the satellite and city even which the two such interest. And the main goal of the work is to specialize the injection holes to obtain internal pockets by the utilization temperatures. This element was the original setting on low power simple subjective to our propellant injector and utilized pockets using a strike chamber. We can see a cross-sectional view of the unipolar working. We have inputs. In a little bit, you can see like simply I have in my hands a big model of my original first. Okay. Yes. My first time is on presentation. You can see the perspective view of the unipolar trust. We have a neutral gas device. We have a gas circulation. We have a premixer chamber. We have a strike chamber, and we have a nozzle. Here you can see another functional cross-sectional view of the neutral system with permanent magnetic and support of the trust. And here we have a casual representation of the electrical push proportional model, which has a dimension of 1, 2. This next figure is possible to see a trusting operation in a vacuum chamber. Also, here an innovation. That's for the first time we have a reliable transfer trust in real time at a balance. The right hand side, we can see as extra flow of the plasma. The methodology was a consolidated physics software performance a similar numerical simulation of the neutral gas density inside the discharge chamber. Two different configurations were tested by a distribution components called normal mode and vortex mode. In this image here, you can see a difference between a normal mode and a vortex mode. With here, you can see here, right, we have mostly 30-degree inclination of the holes. A result, this graph we can understand the color, but we left hand side. Resist. This shows a graph with the same color, but left hand side has a different scale with a maximum of 1.51. And another good graph is Baluri. The orange scale is a 2.5, which 2.05. This indication we that has increased possibility inside the residual chamber. The next graph, we can see the increased density versus axial position. The black line represents the normal mode, and the orange line represents vortex mode. In this study, we were able to see a vortex mode has a neutron gas for a long time inside the charge chamber. The results indicate that the vortex mode has better performance of the valency with a charge chamber obtaining a 43% increase versus the normal mode. These are my references. I hope you enjoyed this work. If you want to read the original paper, please contact the email address. Thank you.
Thank you, Bruno. Sorry about swapping of the names. Any questions?
If you can go back to the simulation slide, I will not explain the answer. I have no, yeah. But when I look at this, I see it's almost the same. No? So can you tell us like why the vortex flow is?
You can see here, and we have same colors there.
Yeah,
Okay.
and the
So you can see here, I have for my
1.5.
red color 1.51. Is the orange color. I have two.
Okay, okay. Yeah, okay. Okay, okay. Okay, sorry. Thank you.
Sorry, what is the unit of this?
Yeah,
What?
it's a flow probably.
I thought it was
Number 8. Number 8. The chamber.
Number what?
Density.
Density.
Is it in per millicubic? 1 per millicubic. That makes sense.
Any more questions? Okay, thank you very much. Now let's conclude this session. The last one, this one is by William Silesio, Design including characterization of technical plasma device for aerospace propulsion.
Hello everyone. I'm William, and today we're going to talk about my work in the lab. I work in the most physical part, so we're going to present this for physics. We're going to talk about the inner structure of the plasma itself, okay? And the work is the design and manifestation of a helical plasma device for crystal fusion. This work is realized with the schema dividers, so you have to select the data. Some for you, I guess, know, and coding random. So the work is divided in introduction, where you're going to talk about the mechanical itself. That was waves that travel in the plasmas. And we talk about the development of the system, the experimental setup, how this works, and the antenna that we were using to excite the plasma. And we have performed some diagnosis in the system that we tell some about the structure of the plasma and how this will be important for us, okay? And some conclusions. Okay, the introduction, we're going to talk about the helicals itself. Helicals are waves that travel in plasma in a very specific range of frequencies. Like you can, and they are responsible for the ionization of the gas itself by our external RF antenna. Okay, so we have the two waves that work in this process. There are the helicals and the digital waves. Okay, they are responsible for accelerating the particles and ionizing the system. And these digits, have some problems that allows a wide range of applications in this for this type of digit. We have electrical propulsion, material deposition. We can make another carbon nanotube do this. Nuclear fusion. We can excite some system and some medical applications. Okay, you do more investigate later. So, what are you talking about here, folks here? And the different generate a very specific type of plasma that is a high electric that have a high electric density, around 10 to the power of 30 per millicuries, and low temperatures, UVs, like 1 to 20 electron volts. Okay. In our laboratory, our focus is two now, and we are growing with this project. So we are in the process now. This is experiment. So we have the idea of electric propulsion in the helical plasma cluster. Okay, where here we are going to investigate the features of the system and something like this, and the material deposition study. We want to create carbon nanotubes and doing some material research with this. Okay, we can assemble some samples and this good stuff. So this is an experimental setting of the system. The chamber consists of two glass tubes. One is the dispersive chamber, where is the diagnostic will be made, and we have the ionization chamber. The ionization chamber have a gas field in this direction, and you have and this tube is enclosed by two magnetic coils, okay, copper coils, that will give a magnetic flux for the gas, and we have a external RF antenna, okay, that will start the discharge and will ionize the gas. The antenna format, we have a very specific shape for this antenna, okay. So we are using the helical loop that is two loops and a third, okay, in the system. So to do the different, we need a very specific. We need to copy our signal from the antenna to the particles. To do this, we need a magnetic flux. These flux don't need to be much intense. You can reach the discharge with a few gauss. I have read articles with 70 gauss can make the t-shirt. But For our purpose, that propulsion, we need a high intensity for this field. So, like you can see here in the simulation, we have a high intensity here that was expected. the coils are here, but we can reach around $350 with this configuration. And we need a very important thing for the propulsion, that is the creation of magnetic nozzle, like the helmet and like the other propulsions or other propulsions of this type around the world. So, like you can see, we have the formation of magnetic nozzle here, okay, and I will show the magnetic nozzle in the system working. This is the field that our coils can reach. Okay, so the configuration that we have simulated is reach about this area, corresponding to 20 amps of current applied in the coils. Okay, so this is the configuration of the throttle. Like you can see, we have two areas where the field is more dense. This is the center of the coils, okay, and where the particles will be confined, okay, or concentrated here. And we have some, and the objective is that the particles get thrown to this direction, okay. So this is the system work, okay. We have here you can see the areas with more plasma, more intensity of particles and ions, sorry. And we have the magnetic nozzle configuration here. The coil was a little back because we have this flange here that possibility the photo. So, but you can see the formation very, and the plasma being far away from the ionization chamber. So the investigation that we made is more preliminary one, because we want to have a notion that what's happening in the ionization chamber and in the initial special chamber. Okay, so we take some diagnosis in the electronic density profile and the ionic density profile. Why it is estimated? Because we have it using electrostatic probe, and the measurement is not direct. We have to do some calculations to estimate this ionic density and the axial plasma potential profile. Okay, so in the next graphs that we will see, each point corresponds one of these curves. Okay, this curve is the hyperactive curve, and all the plasmas that we work that we will base in our life can return one of them. Okay, this is made by three main regimes. That is the electron and the ionic saturation regime. Here we have a appearance being collected by the probe purely of ions. Okay, a transition regime where we have a of two types of currents. Okay, and the electron saturation current regime that is a regime where just the electrons are collected. Okay, there are the values for this purity specific. We have a very usual plasma potential around 36 volts. This is the 36 volts. This is the value that you usually see. The electron temperature is around to 4.72 electron volts. This is, I guess, here like this. We have a high density like we expected, and now ion density a little higher than we would expect. So this is the axial plasma profile, okay? The potential plasma profile, and we can see here that we have a decreasing behavior of this profile. That's what we want. we want, okay? So we want to investigate the structure of this puzzle profile because we have some structures that can be appeared in the religion that have some descriptions, okay? But I will talk some about it later. But we have, we can perceive some interference to the RF signal here. Like you can see the quantum potential is going, but you have a point outside. This is because of fluctuations, okay? So the RF is very hard to work with the bottom because it's everyday marking, it's dynamical variable, and that's it. So this is the axial profile density, okay? So we have the fullest linear, we have a very linear behavior, like you can see, tends to be uniform, but we have some fluctuations to the head. But like I said, is the expert one that density, and the most what this is the interesting thing because we have here isolated ionic density very higher than electron density. This indicates that ions are being concentrated near the antenna. Okay, so this can indicate two structures that is the ions are not thrown. So what we want to throw away much more, but to can indicate to a formation of a structure called double layer. Okay, and we need to investigate more this structure because have some discussion of the impacts of this structure in the propulsion itself. Okay, and that's it. So these are the preliminary results, and we have the the ionic test profile. In this case, that ions are considered very big antenna, but little. We have the with the lower electron density, the higher ion density, with the drop in the potential, hence indicates that we have a high electron ejection, but they don't are ejection or we like, and a formation of the double layer. This is need more investigate, like I said, we need more diagnosis in the blood. We need to further up. We need to do we need to investigate with spectroscopy and some other things. And the system, but the system was reached. I don't mention it; it's here because it's not my focus. But we have performed some previous simulations of the system, and the boundaries are validated. Okay, so we are using for this simulation, I guess the software Showpic. It's a particle cell simulation that was performed by one of our colleagues that are not here, Elan. And the reference of work. Okay, so and think my work. I like to teach the founding organizations, the university, and all that. Thank you.
sense of precision balancing for.
Yes, and making the proper calculations, because you're measuring in grains, milligrams.
Yeah.
So you have to
Okay.
slower than distracting from manual probes.
Yeah, oh yeah.
The error bar is a lot sharper.
Okay, great. Okay, so this concludes our session, and I think we will straight to the next session because we're late. So I pass the microphone. Victor.
I'm Victor, Fuchs from Tech in the front, and I'll be your chair for this session number 6. So our first presenter is remote presenters from UFMG. The type of presentations are analyzed in electromagnetic support, and the leader is Maria Cecilia Pereira. Yes, please go on with your presentation.
May I start?
Yes, we are hearing you clearly.
First of all, thank you for listening to me. I would like to thank a lot the team who has provided the means for this remote presentation. It would be lovely to be there with you, and unfortunately, we had some last-minute issues here. Thank you, Eduardo Bezerra and all his teams for the effort for us to be presenting here remotely anyway. I would like to present here the orbit analysis and design for an academic satellite. This work was carried out mainly by Rafael Guilherme, and I was the advisor. First of all, some words about the PDQ-SAT project. It's our first satellite in Federal University of Minas Gerais. PDQ stands for pão de queijo. That's some food that's really regional and traditional here. And the objects of this mission is technological demonstration of some lithium sulfur batteries that have great energy densities and have proven to be an option for aerospace applications, and also to demonstrate the capabilities of a micro supercapacitor that's being developed and built here at our university. It's a 3U CubeSat, and we are making a huge effort to develop all areas here at our university. The objective of this work is to have a comparative study of different optical configurations for this same, and as we see later, it was not critical for this. As for numerical propagation, we used the J4 and the H-pop propagator, both with solar radiation pressure effects and without. For the atmospheric model, we used MSISE 1990, and we simulated the influence of this, assuming that the re-entry would occur less than 200 kilometers altitude. For the communication scenarios, we included both downlink and uplink scenarios. By that time, we didn't know, and to be honest, for now, we are not sure about the need of uplink signal. And we evaluated a minimum elevation angle between the mission segment to see if it fits the quality and quantity of the information we want to transmit. We defined the minimum elevation angle geometrically, but then we saw that we would have. We know that the lower elevation angle will increase atmospheric absorption, mainly in troposphere, and so it was also an issue that we thought about while analyzing the results. We count for atmospheric losses, and we know that in lower angle it will lose even more, and that's another thing we had to consider. And so with this, we thought about transmitting data for a minimum elevation angle of 20 degrees. And here's some specification for the hardware we use. It's an ISIS, UHF downlink, VHF uplink transceiver, the same antenna. We selected this due to the proven site heritage. It was one of the first choices of our project. We were making the TTNC as conservative as we could, so as to make sure the communication would work. So it's more imposing requirements for the subsystems than working with a compromise between them. We know that the transceiver supports from around 0.5 to 4 watts power. We have the downlink frequencies, the uplink, the modulation, and I will be talking here more about the orbit, since this communication thing, it was not me who was doing, but the basic data is there. The data transmission rate was 9,600 dps, both for uplink and downlink. And using the literature, we thought of 55% efficient of the antenna. So we have also commission off the shelf hardware for the ground station, and it's also from ISIS. We had the transmission frequencies working with the embedded ones and the transmission power, and everything was seen to fit the embedded hardware that was chosen. We had to analyze the electrical supply scenarios, and we calculated the power budget using mainly SDK software, and the software itself helped to evaluate the effective area that was illuminated by the sun. The 3U CubeSat model was created in SolidWorks. It was recommended by one of the literature we used, and for the solar panel characteristics, we used this one from DHB, but for now we are thinking about another one. It's not bought yet. Before simulating, analyzing, we had some considerations to be made. We didn't have all still now we don't have all the subsystems chosen and purchased. So in the sense of the specific power consumptions, we had a generic methodology used also from the literature, and also doing some research in generical numbers for that. The goal was to ensure that the CubeSat subsystems would meet the power demands without exceeding acceptable limits for the APS and looking deep to the depth of discharge. The worst case battery discharge scenarios were used to evaluate the operational orbit. In case it was not attending, we would take this option off the table. And we used the power consumption for each subsystem based on nominal operating power and duty cycles for illuminated and fixed periods. One of the references we used for these numbers we came up with the work of Capelletti. The estimated power consumption then was less than 3 watts during illumination and less than 2.5 during eclipse. The opto period and eclipse illumination times were calculated using the opto parameters for each option. The ellipse and illumination times are derived from equations involving opto radius, angular radius. It was leading to the energy consumption that was estimated over each orbit. The values allow the verification if the solar panel generation is sufficient, and if no, and if the depth of discharge of the battery would not meet the requirements, we would simply take this orbit out of the table. We had simulations for all those semi-major axes and inclinations that we showed, but I will show you some graphs, only some of them, and then I will give you the whole results of the series of simulations. And so we see that using the J4 propagator with the same major axis of the altitude of 400 kilometers and inclination 0, we could see the eccentricity was changing, mostly increasing, and we had more than 180 days of operation that was just right for our mission. If we use a more realistic propagator, we see that in fact the eccentricity is varying, but not so much, and we have a little more than 160 days. If we choose another inclination like 50 degrees, we have again more than 6 months of mission, and we can complete the requirement of the duration of the mission just by changing the inclination. Using J4 and H4 propagators for orbits above 500 kilometers show decay times exceeding 1 year, and so all of them are good for us. For 400 kilometers altitude, the decay times range from 160 to 270 days, depending on the inclination. We saw the H4 propagator reduces the CubeSat optical time compared to J4, and we know that the modeling of the atmospheric drag is more precise, so that's more reliable data. If we have orbits with inclinations below 40 degrees and 400 kilometers altitude, the time of mission is not met, and so it's not an option for us. We consider solar radiation pressure in HPOP simulations, and we saw that it was negligible for the decay of the satellite. We saw that this result aligns with other studies where for small satellites, the solar pressure radiation was not important in this phase of the mission. For data budget analysis, we could see the simulated communication windows for 6 months was met with initial 20 degrees elevation angle. It's sufficient if I want to transmit more than 1 mega daily, and if I adjust for 10, I can do it. For the link budget, the communication times and the revisit times analyzed for various altitudes and inclinations were analyzed. Low inclination orbits will maximize communication time. Near polar orbits become close as expected. non-equatorial orbits above 500 kilometers meet the daily transmission requirement of 1 megabyte. If I have lower orbits, I have longer eclipse periods, what's to be expected. And so it's critical for battery discharge management. The power generation profile at 400 kilometers and 700 kilometers will show minimum variation in magnitude, and 400 kilometers is the worst case scenario. Simulations for 400 kilometers orbits will show a varying orbit for power generation. We have the graphics for those two in a complete work. But if the inclination is 45 degrees, it generates the least power due to extended eclipse time. Minimum power generated during orbit is a little less than 3.6 watt hour compared to a total consumption of 3.45. What means that we don't have a safe margin for that. And that's the reason we are thinking about another panel. And the power budget is viable for all analyzed orbits, but with this very, very small safe margin. We will need a battery capacity of at least a little more than 5 watt hour with 30% depth of discharge. It's feasible with commission off-the-shelf options. And the results show that those in green are viable orbits for us. We can see that equatorial orbits are not good for us. We don't get to harvest the energy we need and or transmit the data we need. And for 400 kilometers altitude, only 40 to 50, less than 60, to be honest, inclinations give us the conditions that we need. So in conclusion, the mission is deemed viable in terms of the duration, communication capacity, energy feasibility across many orbits between 400 and 700 kilometers. The flexibility of the mission is enhanced by accommodating various optical inclinations. If we have an opportunity to launch in many different feedback launches, so we will be ready for many of them. The key outcomes include the establishment of validation procedures for the mission decay, data and link budgets, and solar panel power generation. We didn't want us to think about the gravitational aspect of it, but we wanted to see the main engineering aspects as well. So we could validate the mission once the components and the personal conditions are defined. When we design further the other subsystems, we come back to these orbits and we see if all of them attend what we need. If no, we take them off the table and keep the rest. I will be presenting another work that you'll see that 2 of them are better not to be used after further analysis. I would like to thank the Brazilian Space Agency for funding this project and for this very work, ANACOM, that provided us with the SDK software for some months in order to carry out this first analysis. The main bibliography can be seen here, and if there are questions, it will be a pleasure to answer them. Thank you for your attention.
Thank you, Maria Cecilia Pereira, for the excellent presentation. So I'm opening up for questions. If you have any questions.
No better.
Good morning. I was wondering if you can, in the model that you use for orbital decay, if you can introduce some kind of drag compensation, like in our case, of electric thruster to compensate the drag, extending the lifetime of the CubeSats or enabling other kind of mission, extending the time that the postponing the time that the CubeSat was going to re-entry.
I'm sorry, I didn't listen to you very well. I heard something about considering the drug, but would you please ask again? I'm sorry.
If you in your model that you use for the orbital decay, you can you put some kind of drag compensation like a thruster in your CubeSats, so you can extend the lifetime of it in space. Can you model that? Put that in your model, or it's another model to be relaxed. So you can simulate that kind of decay.
In this very work, we considered some main, let's say, effects. But for example, some details were not added because it was a very preliminary work. But all the simulations are saved, and as we see fit, all the implementations should be done. We are studying further. But in this case, we didn't know very much. You'll see, I will have another presentation about the detumbling of the satellite. As we knew more about the satellite itself, we would revisit the model and see some of its results. For example, in the next work, we know that the mass will be even less than 4 kilos. We know that we know more mass properties of it. And so we run the simulations as we have more detailed things. But for the model itself, for that the environmental model itself, we are considering mainly the atmospheric drag and the eclipse and illuminated time. It's all we are considering then, but as the work progresses, we revisit the simulations.
Yes, thank you.
Did I answer your question?
Largely, yes, but I will make a follow-up email so you can talk more about this kind of simulation.
If there is, maybe, I'm not sure if I'm understanding you since the sound is not so great, but I can provide my email address, and so we can talk about other questions if you think it can be profitable.
That will be great. Thank you.
In my next presentation, I'll
Good morning, my name is Diana. I'm part of the ops team of the European Sat mission from AP, and I'm here to talk about academic research that was made to the mission. The title of our work is Evaluation of the Disturbance Effects Capable of Altering the Orbit of the European Satellite. Here we have our summary, its introduction, objectives, methodology, resumes and discussions, and the conclusions. So, about the introduction, everybody knows that the preservation of the forests and biomes is extremely important because they maintain the balance of the planet. And the INPE is now operating satellites with the main objective of monitoring resilient forests and biomes. And all the missions have a lot of subsystems. One of them is the ALOX, that is our subsystem, and we are responsible to keep the satellite as close as possible to its reference trajectory. The objectives of this work is to evaluate the behavior of the perturbative force and deviations caused in the orbital elements. In the absence of these perturbations, the satellite would be perfect. It would develop a perfect Kepler orbit, and it's not necessary maneuvers to make correction or transfer or whatever. But in practice, it's not true because this force exists, and we need to measure this force, and we need to know how the satellite will behave in its orbit. About our methodology, we use to this work the spacecraft trajectory simulator, and this is an orbital trajectory simulator. In this simulator, we use continuous propulsion and closed loop trajectory control. In the orbital motion dynamics, we just use the solution of the Kepler equation. And about the perturbations, we selected the most important perturbations to our case, and that is the Earth gravitational potential, gravitational attraction of the Moon and Sun, solar radiation pressure, and atmospheric heat drag. About our simulator, the spacecraft trajectory simulator. Obviously, it's an orbital trajectory simulator that uses continuous propulsion and closed loop trajectory control. With this simulator, we are capable of simulating impulsive and low thrust maneuvers. This simulator operates calculating the states of the spacecraft at each step of the simulation. We can consider disturbance. We can consider the constructive aspects of the spacecraft and the nonlinearities of the actuators and sensors. And here we have a diagram, and we can see how our simulator operates. The orbital motion, how can I say it? We just use the solution of the Kepler equation at each step of the simulation, and this step is one of the input parameters in the simulator, and we have an initial state and a time interval. The Kepler elements of the orbit, we obtain these Kepler elements using the basic equations of the orbital dynamics, and we can to make a correlation between these Kepler elements with the states of the variables. Using the Kepler equation, we propagate these Kepler elements, and we can obtain the new Kepler elements in the time interval. And using again orbital dynamics equations, we obtain the state variables in function of these orbital elements, and this cycle repeats to each step of the simulation. About the orbital perturbations to the geopotential and gravitational, we use this model, and this model is based in the most famous equation of the potential gravitational standard in spherical harmonics, the gravitational attraction of the Moon and some we just use the Newton gravitational attraction law because we consider the moon and the sun like literally bodies. To the solar radiation pressure, we use the set of equations, and about the atmospheric drag, we use this model, and this model is just a MATLAB. About the results, first, we will talk about the selected art. To the selected art, we will see about the ortho perturbations and the variation in the ortho elements. The selected art. So, the arts of the BioSat, the satellites of the BioSat mission, until now is not completely defined, but we have some characteristics. The art is sun-synchronous and the altitude between 550 and 660 kilometers. And that is what I need now. To the situation as a synchronous art and this altitude, we have an infinity of possibilities. And here we selected one to make our analysis. And we select a data two, and this is not a provision to the launch, this is just my birthday. To the ortho perturbations. Here we have the geopotential perturbation in this axis. We have the delta V due to this force, geopotential force, and here the time of the simulation. For this case, we have one thing. Look for these magnitudes. And in the pictures, we can see a lot of colors. Each color is one axis of the vector of the delta V due to the force. And the pink line is the resultant acting on the satellite. So here we have the geopotential perturbation, here the solar attraction, look the magnitude here, and the magnitude here. Here we have the lunar attraction, and here the solar pressure radiation. Here the drag, and here the total perturbation acting on the satellites together. And look the magnitude. So with these results, we can see clearly that the most significant contribution is the perturbation due to the Earth's gravitational potential. And it's for us, it's so good because this force is acting by rotating the Earth plane. So in this case, that we suggest, the rotational gravitational is working in favor of our mission. In this case, we don't need the corrections in the right extension of the assembly code. And all the ortho elements that I'm telling are the same that Professor Talita showed us yesterday, maybe here, in a beautiful picture. She appointed just the brand for us. So we don't, so for us, it's very good because this force is helping the mission. But this force is always acting also in all the ortho elements, not just in the runner. And all the others, perturbations are acting on the all Keplerian elements. And maybe it can be necessary to make some maneuvers of correction in our satellites. Here we have the sum of the velocity increments, the sum of total perturbations. It's just the value of the velocity increment acting on the satellite during each step of the simulation. It's a sum for this alignment. Here we have the sum just to the geopotential perturbation. It's not good, sorry. And here we have the sum of the other perturbations, excluding the geopotential. Looking to the magnitude and looking to the magnitude, we can see that the geopotential is strong. But including this force, we have a new winner. The moon is the first force. After we have the sun and SRP and the drone. It's for our case. If we change the initial condition of the simulations, it can change too. The variation in the elements, because this course cause effects in all the elements because they are acting simultaneously on the satellite. Here we have the centimeter axis and the time, and we can see that the centimeter axis varies due to the variation in the eccentricity. In inclination, the variation is small, but it exists. And here we can see an important characteristic of the sun-synchronous orbit because we have a variation in the rank of 0.98 degrees. And this is a beautiful characteristic of a sun-synchronous orbit. So we can see that the orbit selected for this stud is a good orbit for our satellite. The conclusions. So we evaluated the perturbations capable of altering the orbit of an artificial satellite with the characteristics of the Yonaguni mission. We saw that this force impacts the satellite's orbit, and we have variation in all the orbital elements. The most significant perturbation is the geopotential gravitational, but the other perturbations exist and they are important too. And finally, we conclude that it's important to evaluate the perturbations that acted on the satellites because we can help with the dimension of the capacity of the propulsion system because can be necessary to make some orbital correction maneuvers or something, and this is important to guarantee the success of the mission. We would like to thank the INPE and CNP, and thank you for your attention.
I will keep presenting about the PDK-SAT, and now I will talk about the 3 UCubeSat, the tumbling simulation and control. I will say something briefly about the project again, the objectives of this work, and then I will go through the operational attitude, methodology, dynamics and control, the results, numerical simulations, analysis, and conclusions. Well, again, it's our first satellite. It's for the technological demonstration of a battery and a micro supercapacitor. It's a 3 UCubeSat, and we are making an effort to develop everything here at the university. In this work, we aim to analyze and simulate a B-dot control law for satellite tumbling. And we didn't have many requirements for the operational attitude. We wanted to detumble it and to have it as close as possible with a minimum effort of the operational attitude. But our operational attitude is not very strict because only the communication requirements are taking place here. The -z direction is pointing to Earth. So we have pitch and yaw kind of free because the only thing that's having a say here is the communication. And we have a restriction in yaw, but only for velocity, and it's not very strict as well. For carrying out this work, we had simulation set up where we implemented the B-dot control strategy in MATLAB, and we were analyzing the predefined orbits that I showed in my last presentation. We had the physical properties model in MATLAB as well, and we chose also a convention off-the-shelf magnetometer. It's a 3 coiled with 0.02 square millimeters and 2,000 coil turns. It's the same used by Sham et al. And we had some initial conditions. They were random rotations in the range of -1.5 and +1.5 radians per second. We chose to have the K gain in the interval of 0.0001 and 0.02 with 15% of safety margin. The control metrics was analyzing the system behavior based on the control efforts. We analyzed not only the performance of the control, but how much effort and the signal energy, and also the integrated absolute variation using the trapezium rule. So we could see not only if the control worked, but how much we had to spend in order to have it controlled. And so for analysis, we evaluated the control strategy performance together with those metrics. We modeled the dynamic using quaternions, and here we have the B-dot control law. We have the knee as a minus proportional B-dot, and it can be written in this form since it's B cross product with the angular velocity, and so we can write it as -k B-dot over the square of the magnitude of the geomagnetic field. This K, that's the gain, the literature says that we can use this perimeter that counts on the location of the satellite and the moment of inertia, the minimum one, to start tuning the controller. For this geomagnetic field, we use the IGRF 13th generation. It's updated every 5 years, and so we use the model from 2020 to 2025. Here we have again the 3 UCubeSat. Here we already had updated information that's not 10 by 30 by 10, but 34.5 centimeters. We already know that's not going to weight 4 kilos. It's more likely to be 2.5. And as a payload, we have a homogeneous parallelepiped center at the body. It takes 10 centimeters by 15 centimeters by 8 centimeters, and it weighs only 300 grams. And so the weight of the satellites mainly in the opposite sides of the satellite. The bus takes the rest of the volume, weighing in about 2.2 kilograms. And so this is the moment of inertia that results from the homogeneous distribution of the other parts of the satellites. We had initial conditions, as I said, taking random values. And so we selected some to present the results in the 3 axes of the satellite. I will show you here one case where the altitude is 500 kilometers and inclination is 10 degrees, remembering that we saw that we cannot use the equatorial orbit because it does not attend communication and energy requirements. And if the gain is 0.0005, we have an oscillation in the first 100 minutes, more or less, but then I can take it to 0 with minor oscillations after that. If I change the gain, I can have less oscillations, but then again, I will take more time to get to the 0 angular velocity in the x-axis. And if I get another gain of 0.0085, again, I have in the beginning a small oscillation, but then I come to the velocity equals 0. And so we had this for all that orbits that we showed you, varying from 400 to 700 degrees of altitude, and the inclination ranging from 10 to 90 degrees, and if 400 kilometers, only 40 and 50 degrees. And here another result for another gain, and again, I have less oscillation, only the 10 per seconds, and then I get the stabilization. Well, I had many cases. I will show here some of them, and then I will give you the overall results. For this case, the results showed increasing oscillations in control as the gain increased, especially if the values are high. The system responded more as K approached the extremes of the simulated range. In case B, where we had the same altitude and 20 degrees, if I'm not wrong, I'm sorry, I forgot to put here. The results were not good. The controller wasn't able to manage the satellite initial velocity. It's attributed to the low moment of inertia, because if we changed this, it could control, but of course it was only attached. It's not like we can manage the physical property so badly. But if the speed range was lower, from minus 0.8 to 0.8 radians per second, the controller worked okay. In case C, the same, but 30 degrees, it was required less control effort, and the signal energy compared to a filter case that I will show you, and simulated at different gains, both control effort and energy was presented for each axis. Case D, I had the 600 kilometers altitude and 90 degrees of inclination. The velocities converted to 0, but it took much longer than other cases. And it displayed higher angular speed on one axis during the transient phase, but it neared 0 over time. For the same altitude and 60 degrees inclination, we had more oscillations than case C and the next case that I will present. It needed more control effort, it needed more energy, and the simulation struggled with angular velocity oscillation when the controller wasn't well tuned. We had to tune it better, some cases manually, to get the control to work. Another case, same altitude, 30 degrees inclination. The highest signal energy on the z-axis with a peak current of 2.3 nanoamperes, indicating high control effort for the tumbling in this orbit. Control oscillations were observed, similar to other cases, but when K wasn't properly tuned, and again, if we tried manually, we got some decent control. Overall, as I told you, we simulated all those orbits for many different Ks. And so to wrap up here, the case B, it was a failure. We think it's the problem of the low moment of inertia. It functions within a smaller range of angular velocity, but it's not like we want to limit ourselves if we cannot. And the control effort and signal energy, they do not scale directly with the tumbling speed. In some cases, like case E, it was more oscillatory, so it needed more effort, more energy than other cases. The behavior of the gain, the control effort, the signal energy, and the settling time varied with the gain. Increasing this gain reduces settling time and error, but increases oscillations beyond a certain point, and so we have to choose the gain carefully. There was some tuning issues. If K was too high or too low, the controller failed to the tumble. It was infinite oscillation or high oscillation, and also the current needed to try to control it. As for the convergence, in all cases, the system settled with velocities below 0.05 radians per second after the transient period, but we would need longer observation to show if it would behave better. In conclusion, light actuators like 3-axis orthogonal magnetometers can effectively detumble a 3U CubeSat with properties similar to ours using the BDOT controller. The controller successfully reduced the tumbling to near zero, but faced limitations with high initial speeds during the unusual moment of inertia. Specific issues arose in this very inclination, 600 kilometers altitude, 50 degrees inclination, and gain of 0.0292. We needed to do the manual tuning in order to make it work. Our simulation showed the BDOT controls effectiveness, but for orbits in 600 kilometers of altitude and 90 degrees inclination, due to bad behavior of the controller, and 30 degrees due to high energy consumption should be avoided. We can work in those orbits, but we have better options. Due to our work to explore energy efficient orbits, we could use Monte Carlo simulations to approach these better solutions and finding optimal orbits for the PDK sound. The controller tuning should be further refined based on mission needs and the chosen orbit. And as for now, we have, after this work, we have even more detailed mass properties of the satellite. I was a little concerned if it would work within those cases, but we rerun the simulations and it works just fine, even a little better than the presented cases here. I would like to thank the Brazilian Space Agency for funding, and I have here my contacts. So if you have some questions, you can write me regarding this work or the other work. It would be a pleasure to discuss further questions. Thank you for your attention.
Thank you, Maria Cecilia, for another excellent presentation. So I would like to open the floor for questions. Does anybody have any questions?
Hello, Maria Cecilia. I have a little question, just a curiosity.
I saw your conclusion that you are thinking about moving later, Monte Carlo, to use the Monte Carlo method for optimization. In that.
I'm sorry, I'm not hearing you well.
Can you hear me now?
I'm not
No?
hearing well. If it's not to ask so much, the person who is dealing with the transmission, if they can please type the question here as you ask, it will help me a lot to be sure that I'll understand what you're asking.
No, I'm sorry, we cannot change your slide. Can you hear me better now? Little better?
I can hear, but I'm not sure if I can understand 100% what you're talking about, because we have too much noise here.
No problem, just a second. I'm gonna type it. Okay. Maria Cecília, se puder responder por aqui, responder no vídeo, eu te faço pergunta aqui. My question is.
I'm getting the question here. The person is sending me here. 1 second, please.
Yes, I'm sending you by WhatsApp. Just quick question. You, in your conclusions, you told you were going to be using the Monte Carlo method for optimization. Are you working on that already, or is just a future work?
We are not working at it already, because for now, what we wanted was to dismiss some of that orbits that seemed okay for us to work on. And so we are carrying on other analyses. For example, since we have another mass properties, we want to make sure that as we have a more realistic model, if this approach will work. Since it seems it will work, we have some preliminary results with these new mass properties. And then our next step would be have this Monte Carlo simulations to make sure that we are covering initial conditions that are more realistic to analyze. Thank you for that. Did I answer your question?
Thank you. Yeah, it seems it was answered. Thank you very much. So I think we can proceed to the next presentation if we don't have any other questions. Okay, thank you very much, Maria Cecilia. Yeah, let's proceed to the next presentation.
Thank you all for your attention.
Thank you. Okay, so while they are setting up the slides, I will introduce. So the next presenter is from UFSP or UFSC. Is Felipe Juliano. He will present about hybrid belief system for CubeSat ACS testing. So since we have these slides on, once you get the mic, you might start your presentation.
Yeah, quick. This is and we work from the department as well, and the supervisor is Dr. Carlos for this time. And what's going to go? This is a way to set a test bed for speech control and calibrate planning operators. So these two ways, exactly from how exposed. And here we have a uniform magnetic field in one axis. The idea here is we use three configurations, one per axis, to create a uniform volume of a field and put satellites into this volume to reproduce the magnetic field on the middle of the coin. Here we are mathematical model coordination system. So here we was is the reference of the coin, and the main idea here is you don't have any variation of the magnetic field on the axis. So we use this equation and second derivative equals to 0, and we got the of the x. We got the value of x is a little is 0.5, and this represents the distance between the points. So when you do that, we guarantee you don't have any variation between electromagnetic field constant of the coil. Here is a simulation of the setup for one axis. So here we have one point, and here we have another point, and two red lines represent the area that I can put my satellite. So I have perfect lines here, and I can use it to test at max 3 satellites. But their accommodation and I mean this paper is only one new satellite. Here is the point I talked before. So I have 3 spaces between the points. So it's 0.27, 0.25, and 0.3. And the most fit of the most uniform fit is the 0.7, 0.27. Okay. This curve represents that distance I talked before. So the distance before 2 points. And the uniformity of field with this curve is 0.02% of variation. This is to 1 euro cubesat. If I try to 3 euro cubesat, I got 2% of variation. Here is the electrical parameters of the coil. I made with a W70 and 0.5 meters the coil. The coil has a total length of 1 meter, but I work with 1 meter is 2 levels. So 1 level is 0.5 in the mathematical model. Here we have the loop control system. We have these function clusters for coil, and they work with this simulation we talked about before. And here is a step function response of this situation here. So we have the blue line, the simulation, the red line is the measurement of the neural environment. So we have a little domain in the red line due to leading inductance of the coil is a little more high than expected. Here is control of the coil. It is a operational amplifier, and we got inputs of -10 to 10 volts of the DC here, and we got -2.5 and 2.5 of coherent coils. So we got oversized this to -5 amperes and 5 amperes of coherent coils. Here is the DC noise compared to drive noise. We work with a DC of 16 bits. So the two lines of externals is the AC noise, and the noise measured here by TMM multimeter is the system noise. So we're able to use our resolution of this without velocity. Here is the software loop. So in the system, this system will make the push of the magnetic field to the center of the reference. So we need two line elements in this with satellite configuration. And go to SG4 model. And output of the SG4 model go to WAM20 with a word magnetic model. So I got the magnetic model of the Earth, of the position of the group size here, and I needed to simulate orbital behavior of the group size on Earth. And after I simulate the orbital behavior, I can send the magnetic field for goods. This is the equations that solved by software, by this block of orbital behavior. So we have a moment equations and angular velocity equations. And after that, we have a pattern to represent the position of the satellite on its body. And after that, we have the magnetic fields. But this graph is direct from WM20 that represents this block here. So this block gives us the graph, but it's not happy to put in the equation. We need to multiply by position, rotation of patterns. And when I rotate this magnetic field, I get this magnetic field here. It's a little bit high frequency. But this is the magnetic field observed in the center of the curve. And this is a orbit plotted directly to SG4, this block here. And about precision, this is a low-cost project. So I made the building, the construction of the point. And the requirement for a space lab is less than 1% of precision of uniformity, and I got 0.4%. This is good for the most of the missions, but some missions cannot be tested with this test bed. You need a little bit like box as a limitation risk. You need that to 0.06 or less than that of uniformity feeling. This difference between 0.4% and 0.02% is by living and environment noise of the plot. The people need to be able to counterbalance the interference to variations in the environment. So here we got the test was set on the max value of the code can reproduce. So we have uniformity on one use satellites volume. The same test for a two units volume. I got around 0.9% is acceptable for our environments. Yes. And here is the energy of the center of the curves. So between here at least the distance represented millimeters. So I have minus 16 here and plus 16 here. And the magnetic fields set on central of the curves. And that's
Thank you, Pedro. I have a question. Inside your household stage, how is that like? Is it static or you plan to have some air table or something like that?
Now it's static, but we are preparing for fighting. This rotating magnetic configuration is only for static pulse. And after we apply the table, we need to adapt the simulation for working with a table. And the route is so better for students.
Thank you very much. So sorry for asking the first question very fast. So I would like to open the floor for other people that want to ask questions. Anybody in the audience?
Thank you. Well, it's not a question, it's just very interesting your development. It's just a curiosity. You are planning to use it in a 1U unit, right?
Yes, and this point is one new to start. So we have in the next version we have a argument table. We operate for 3 unit starts for our declaration.
Oh, yes, thank you. Just for curiosity, for the three unit, how big, how much of the space are you expecting for your to
Okay, this coil is 1 meter, 1 meter cube, and is the double volume for 2U and the triple volume for 3U. So you get the same uniformity. If you feel acceptable the less uniformity, you can adjust the volume of coil.
Thank you very much. Congratulations.
Thank you. I would like to ask if anybody else has any questions. Yes, we have a question.
Now I have a little question. So if you want to use a larger, if you want to use a larger satellite to do the simulation, like for you, for instance, you need to make a physical adaptation. So get a big structure, not just mathematical.
Yes, I need a physical adaptation. I need to give it big strokes and that.
Yes.
Thank you. So I think, thank you very much for the precision and the answer for questions. I think, yeah. So now we have a presenter from UFMG, but I'm not sure if he or she is here today. The title, anyway, I would say it's Development and Performance Analysis of Altitude and Orbit Simulator for a CubeSat. So is there anyone around that will present this one? Okay, so in that case, we will proceed to the last presentation of this session. So, we have a recurring presenter from EP. Our presenter is Leonel Gonzalez. And she will present about analyzing of the fuel consumption for orbital correction maneuvers through mitigating injection errors on the launch. So once you have the mic, you may start the presentation.
Good morning again. Good afternoon. Thank you for your insight now. And I will start with my contents. We have the introduction, objectives, methods, results, and decisions, and time and the conclusion. About the introduction. Like I said, EP is working on the research mission. And in this mission, we have a remote sensing with all satellites, CubeSat type in the 12 kilograms class with a dimension of 18. The objectives of the mission is to collect radiometric data of the Brazilian territory in the visible and near infrared bands of the electromagnetic spectrum. To develop a satellite mission, we need a lot of subsystems, including the altitude and earth control system, the AOX, that is our subsystem, and we are responsible for controlling the satellites, earth and altitude. In this work, we have made two objectives. The first is to analyze the possibilities of maneuvers that transfer the satellite from the orbit in which it was injected by the launcher to the normal orbit. And to these situations, we will analyze the full budget because the food is an important and limiting factor in all the space missions. We need this analysis to know if we can or we can't do the correction and transfer maneuvers. In this work, our method is just to know how to calculate the correct and the transfer maneuver and what is the full consumption to perform each one of these maneuvers. We use in this work and in the Geosat mission the most famous maneuver that we know in the earth mechanics, that is the Homo maneuver. In this maneuver, we can correct the major axis with just two maneuvers. Here, we have the insertion orbit, and in the apogee of this orbit, we apply the first impulse delta V1. This impulse transfers the satellite to the transfer orbit here, and in the apogee of this transfer orbit is applied the second impulse, the delta V2. With these equations, we can calculate numerically the magnitude of this impulse. Both these equations we have from this new equation, an important equation of the orbital mechanics. The total delta V, the total velocity increment necessary to realize this maneuver, is just the sum of delta V1 and delta V2. We have another maneuver that is an inclination correction, and we can realize, calculate using this equation, but it's necessary to avoid this maneuver because it's really so expensive. And the total velocity increment to transfer and to correct the satellite is the sum of all the delta V's applied on the satellite, delta V1, delta V2, and delta V3. The full budget. We have a correlation between the velocity increment and the full budget by this equation here. Here we have the length of the full, and here we have the total delta V necessary to realize all the maneuvers. This is the rocket equation. Our results and the discussions. So here we have the possibilities of maneuvers to correct and transfer the satellite from the orbit into which it was injected by the launcher to the nominal orbit. Here we have the delta V used to realize the Homo maneuver. And here we have a variation in the altitude between 500 kilometers until 700 kilometers. And to its altitude, we have a delta V. but here it's just for the home maneuver. And here we have the situation that the results for the inclination maneuver. And we have here in red an altitude of 600 kilometers, and it's for us is an so interesting altitude because with this altitude we can help the camera people. I don't know a lot of these because they just say for us, oh, we need this altitude, and we're telling them, okay, we can do it, and let's go. For them, it's so interesting. For this reason, we are looking for this altitude. In other situations, we consider it as an major axis error of minus 20 kilometers, an inclination error of 0.2 degrees, and an eccentricity error of 0.005. And here we have the total delta V with both maneuvers together. Now, we restricted our output around 600 kilometers because the setting that is an important output for us. Here, we have the maximum velocity increment to realize the home maneuver. Here, the inclination maneuver, and here, both together. And we can transform these maximum velocity increments in full consumption. And we have this number for the home maneuver, and this for the inclination maneuver. And here, the total full necessary to realize both maneuvers. And now we have a problem because this number that represents the full budget is greater than the full tank capacity of the propellant that we found on the market for the satellites in the Eurosat package. And for us, a solution is restricting the requirements for injection error in order to buy the launcher. For the first scenario is to change the eccentricity error to 0.004 and inclination error 0.1 degrees. And we have this situation. And this situation is just for the option. For this, it's a problem. For this reason, it's a problem. And for us, it's a big number. So we have another case with another error for the eccentricity and another error for the inclination. And now we have this maximum fuel consumption, and it may be okay for our situation. And with these analysis, you can see that it's so important to look for our launcher, because if we have a big mistake in our orbit, maybe we can't correct the situation. So we need to select our launcher with many careful. The conclusions about this study. We have a preliminary study, a preliminary analysis about the situation. With this study, we present the possibilities of correction and transfer maneuvers, and now we know that a good choice of launcher is essential for the success of the mission. Again, I would like to thank the National Institute for Space Research and Thank you for your attention.
Thank you, Aline, Leonard, as well as for a lot of excellent discussion.
Thank you.
So, we're gonna move now for the questions, so I'm opening the floor. Anybody in the audience have any questions?
Yeah. Thank you for the presentation. I just wonder from this science point of view, do you have like very stringent requirements on the altitude or the resolution of your camera? That's
The altitude?
yeah.
The phone?
Yeah, because why do you want to control so much the altitude at this high precision?
Because it's a result of the camera.
Okay, yeah.
I have a call I think 30.8 degrees maybe, and we need to have 40 kilometers, I think.
Okay. Okay, so that's thank you.
Thank you.
For the question, so do you have anybody else that wants to ask any question about this issue? Okay, that's all.
experience.
Podemos iniciar?
Se precisa de teclado, eu quero pegar aqui. Vai ligar. E aqui vai tirar uma parte da outra de não, não, mas vou responder outra Sai 11h30 à noite, 11 horas. Vai direto. Olha, boa tarde. Uma coisa. Se a gente vai para Guarulhos, fica uma hora lá, embarca de novo, e depois amanhã chega às 2h. Mas eu gostei. Uma hora. Você vai mais tarde, acho que vai chegar mais cedo. 8 horas cada uma hora. Amanhã? Amanhã. Eu fui remarcar, mas.
A última funcionar, será que agora foi?
Exatamente. Qualquer coisa, assim, tudo aí mesmo.
Good afternoon. We are going to begin our afternoon session. So please, I would like to invite Victor Schultz for his presentation. Victor, thank you very much.
Thank you for the invitation. Yeah, I'm Victor. I work in Japan at the Kyushu Institute of Technology. Short is like QTech. And yeah, I work in this LACW laboratory. And the title of presentation is Empowering Global Collaboration. So I will collaborate with you. So please, if you find anything interesting, I'm going to throw a lot of information. Let's talk later about it. And also I'll talk about the opportunities in Japan's space engineering and give some developments at QTech. So yeah, it's a pleasure to be here. I was very happy to be invited by Professor Bezerra to come to the conference as keynote speaker. Thank you. So yeah, let's talk about QTech. So what is QTech? So QTech started in '97. It is a private institution, named as a private institution at that time. So it was a college of technology. And then, yeah, these two guys are the founders of QTech. And the mission of QTech is to cultivate students with integrity and creativity for industrial advancement of our nation. Well, I'm still here, but I'm referring to So QTech, we have 2 campuses, 2 undergraduate schools and 3 graduate schools. We have about 6,000 students, 400 faculty members and researchers. One of them is me. And we have admin and technical staff. We have 305 international students from 42 countries and regions. It's interesting. I'm having trouble with this process. What? Okay. Let's go. No. Você pode passar o slide, por favor. Okay, so here, so where are we in Japan? So here is Kitakyushu City. So here is where the Tobacco campus is of QTech, which has this nice main gate for the entrance. So it stays 1,000 kilometers from Tokyo. So it's quite far away from Tokyo. So actually, capital of South Korea, Seoul, is closer compared to Tokyo. And the population of Kitakyushu is a very small city for Japan with about 1 million. Then, yeah, we have not only Tobacco campus, the one I told you, but we also have Wakamatsu campus and Izuka campus, so they call this triangle. Everything is around the region of the Kitakyushu city. So what differs is the schools. So some schools are in different campuses. And then in the Kitakyushu, also the Kyushu Island region, so this is some photos around the region in the Kyushu where our university is. So you can experience things like 4 seasons, like below winter and so on. But yeah, we have this castle there. This is like Kokura Castle. It's like a traditional Japanese castle. It stays in the center of the city. So if you go to some mall in the city, you look from the window, you see a castle. This is quite interesting. And we have also a lot of presence of industry there in Kitakyushu. We have some museums, art, science, and a lot of cultural heritage. So yeah, this is one of the festivals they have in the Toba region of Kitakyushu, where they have this kind of pyramid made of lantern. And there are people inside, which is quite cool. So that's cool. Next one. So this is how our education works. So yeah, it is very like hands-on practical education. So the students join the laboratories and they learn within projects, starting from the final year of the undergraduate program, and then on master and doctoral programs. So we have in QTech these 6 centers, research centers and units. So the one I come from is called LACW, it's Laboratory of Link Satellite Enterprises and In-Orbit Experiments. And then we have other 5, so we have about Energy and Environment Center, we have AI research, we have IoT, we have something like a robotic and power electronics, other centers. And then now I will enter talking about the LACW laboratory itself. So this is our mission, to bring diversity to the space sector and contribute to space activities through CubeSats. So because we want to bring diversity, here is not just about the people or where they come from. It's about industries. We want to bring new companies that want to join, like create something in the space area, so the new space. But also about countries, we want to countries to have capability to launch satellites. So it's very broad concept of diversity. Then the importance of the nanosatellites, I don't have to tell you, but basically the one that is relevant for us is this one, increasing diversity in the space sector. So through the low price, you can take more risks and do new things. And yeah, new people can participate. It's the most important. Then let's continue. So what is democratization of space? So here we have this map. Maybe it's hard to read from the back of the room, but if you look at the well-developed countries, you're going to see thousands of satellites launched. But you can see that there are newcomers and many countries are launching new satellites in Africa or in South America and so on. So it's creating some kind of democratization. And the idea is because mainly less cost. This is the main one, but also like less development time. And we have more mission capabilities as the technology evolves, and we can use standardized cost components. So this is how proliferation of nanosatellites is going in the world. I'm sorry, this is a bit old data, but before 2012, 21 countries had launched one satellites. And then in these 3 years, 13, 14, 15, plus 17 countries entered in the game. In one is here where we are. And then from 2016 to 17, in all same period of 3 years, then other 25 countries enter into the non-satellites and they are launching their satellites. So, and from this people entering satellite, non-satellite industry, for the countries, many of the countries, it's their first satellite off. So they start their space program to a CubeSat. So you can see since 2017, 25 countries had their first national satellite as then I'll change a lot of the subject in this presentation because I want to collaborate in many areas. So now I'm going to talk a little bit about opportunities for studying in Japan. So in Japan, inside our LACW laboratory, we have these Space Engineering International course, SEIC. So SEIC is a course that is not for undergrad, it's a master and doctor course. And this course it started in 2013 to as a graduate school of engineering in UTEC to support the PNST program from the United Nations. And the idea is these 4 pillars: research toward master or doctoral degree, this on-the-job training, such as space environmental testing workshop, this project-based learning. So people learn by joining a project, and inside the project they get a lot of knowledge. And space-related lectures in English. So this is a part of SPIC. So many people ask me like, how it would be in Japan if I went to Japan? How is the Japanese language? And I was tell, relax a bit because you can go to study in SPIC and all the classes are going to be in English. You have a lot of support people from the staff that speak English. You also have one of the Japanese students in the schools that we asked to help you to make your bank account and documentation when you go. So we have a lot of structure to support people that want to go to Japan and learn their in the SCIC course. And this important thing, we can do also work not exactly only in engineering, but also in space policy and other areas. But it's an engineering school, so yeah, the strongest point of SCIC is social engineering. And yeah, it's a very multicultural environment. So the statistics I remember is that about 60% of the students of SCIC are not Japanese, so they are from all over. And yeah, if you're interested for studying undergrad development, there is a scholarship opportunity called PNST. So you can search about it. It's one way to have economical financial support to go study there. So yeah, I was talking about the different countries. So we have, of course, many people from Japan because we are there in Japan, but we have people from many other countries like Thailand, France, China, Honduras, Indonesia, Nepal, Vietnam, Mexico, Cambodia, Laos, Mongolia, Egypt, Palestine, Algeria, Ethiopia, Nigeria, Sudan. South Sudan, which is a different country than Sudan, and I learned when we listened to South Sudan. Rwanda, South Africa, Trinidad and Tobago, Zimbabwe, Uganda, Thailand, Turkey, Brazil, and Paraguay. Yeah, we have one Brazilian student that is not me because I'm staff, so there are 2 Brazilians there. Okay, so this is that data I showed you before, but represented in a map. But also included graduated students. So the graduate students are the countries in blue, and the countries in red are we have currently people studying there in UTEC. Yeah, this is from April of last year. And yeah, because of this very global distribution of the students, we we this kind of award from, in this case, from Minister of Foreign Affairs of Japan in 2017. Then I think when I talk about LACW, the most famous program we have is this BIRDS program, is a satellite program. So it goes from BIRDS 1 to 5. Actually, there are others. There is also BIRDS X and maybe a new one starting called BIRDS PR. But originally it was going to be 5 programs, and then we are extending a little bit. So the first program was 5 satellites from these countries here. Then we have the BIRDS 2, BIRDS 3, BIRDS 4, and BIRDS 5. So when I went to Japan, I arrived when they were finishing the BIRDS 2 and starting the BIRDS 3. Then, yeah, I met people from all these countries, starting from BIRDS 2. So Bhutan, Malaysia, Philippines, yeah, many friends from Sri Lanka, Nepal, Paraguay. I met many Paraguayans there instead of here, which is interesting. And Philippines, Zimbabwe, and of course, many Japanese also part of this program. And the program features are already explained about the number of satellites. So there are constellations, just 5 or 3. And they are built by students. And the program lasts 2 years from concept design to disposal. So in 2 years, the student can go through all the process from starting with the concept, thinking about what mission I will do. Then they start to build their models, and then they go all the way up to the launch of the satellites. And then they start to operate the satellite. So they got the amateur license, and they go to the ground station and operate the satellite. So they can see the satellite re-entering at the end. And they learn all the process. And yeah, we have this network operation by multiple ground stations. So one thing we do is that from these countries, we incentive them to make their own ground stations so they can operate as their own countries. Yeah, this is another award we won for diversity from GDC Airbus for the first project. We have also won the award from Paraguay, this National Order of Merit Jose Falcon. And yes, this is because of the BIRDS form when they did this learning satellite, which is their first national satellite. So they started, in a way, their space program with satellites in this province. And also, yeah, QTech has this award, Small Sats by the Numbers, from this breakthrough technology. We won because between 2018 and now, in 2024, we are the world number 1 operator of academic small satellites. Yes, so I have this graph here. So you can see this first university here in the world for small satellite launches. And the second one is Technical University of Benin. So yeah, we have some competitors, but we still are number 1. Then I'm gonna go through a quick review of the QTech satellites. So these are developed in our laboratory. So starting with like not one satellites, but a little bit bigger. So we have 4U1, 4U2, 4U4, and this SN2, and then our LOX 3. Then around here, the BIRDS program starts. So in 2017, then we have BIRDS 1, BIRDS 2, the Spatium satellites, TENCO, which is a bigger one. Then we have our LOX 4, BIRDS 3. This is the time I arrived in QTech, so here I start to see it. BIRDS 4, Futaba satellites, Kitsune 6U. This is the first satellite project I joined. This is the delivery date. So I joined in 2019. And Mitsuba and the BIRDS 5 here. And now going to 2024, in this year, we have these Curtis satellites, 3U, micro-orbiter 1 satellite, BIRDS X, so BIRDS is still continuing. So BIRDS X already finished the attempt, but it's not launched yet, so everything from the right which is not launched yet. So the students are also doing Yotsuba satellite, Leopard satellite, and Vertex satellite. So at the moment I'm involved. So these 2 are already finished operation, Curtis and micro-orbiter. and I'm working directly on this low carbon Arctic satellite. So now from the satellites, I have more experience. I will try to show quickly some information about them. So this is Kitsune satellite project. It has been developed by collaboration between academia and some private sector in Japan. So we did it. Also, Admix Corporation is a harnessing corporation to Japanese companies. This NTU University and the Arthur C. Clarke Institute for Modern Technology. So these two universities also have partnership with us. The name of Kitsune means this very long thing. You can read, I will not read out loud. And but Kitsune, the word Kitsune means fox in Japanese. So actually, it's a cute name. Japanese people. And Kitsune is very interesting because it's almost like it's two satellites inside one. We have two buses inside one satellite. So the reason is this one, frequency coordination, because there were some missions that fit to the amateur frequencies, and some other missions did not fit, so we had to split it into two buses. So the only thing that is shared is the EPS. So battery and solar cells, they are shared. And once we get the raw voltage line that's going to feed the satellite, it goes to different buses and they don't talk to each other. There is no communication between the two buses. So you could completely separate between one computer and so on. So these are the missions. So we were improving our bus system because we are scaling up from the first 3 satellites to 6U size. Then 3U camera payload. So half of the satellite is a big lens and camera system. So this can take a 5-meter ground radar. Cool take. And we were also experimenting C-band communication in amateur radio service. We also have this total electron content measurement in ionosphere, CSAC demonstration. This is chip scale atomic clock. So we have an atomic clock inside this satellite. Star and forward mission and a lot of demonstration. So and also this is linked to the next one, ground station terminal capacity building developing country. So for this two, yeah, this satellite can be star and forward, increasing the lot of frequencies. And it can have EPSs all over the world. So for example, in Latin America, in Canada, we have some EPSs that could translate to the satellite using the then another satellite I worked with is Curtis. This one is one project that I'm most happy about the business because we work at Panasonic company. It's a big company, Panasonic. Everybody knows about Panasonic, but they are in satellites. They have no knowledge at all because they're just starting. Very and yeah, we did these missions, orbital exchange. So we had some Earth's left side here, where it was very key to the other side. We have high detection price of OBTPS that you check in a single void. So we only want to this resolution image providing medical analog camera. We will show you some photos later. And yeah, it was like so ISS or so this is my favorite picture because we took this picture 12 seconds after release from the International Space Station. So you can see here is the keyboard module. They have this J solid deployed, and this is currently satellite as seen by the ISS. And this is the ISS as seen by the Earth. So this is one picture. And this picture was downloaded yeah, so this 12 seconds, 10 seconds is the time it takes for the payload Linux to boot. And the 2 seconds is the time that it takes for the OBC to understand regional flash memory, understand that it should take up to that time. So it's a switch that you can have and this is another example of picture taken from over the Kansai region on the map. So what is interesting here is not only the picture itself, but the way we So we have some multispectral camera instruments. So the people we want to take photo of the something like sunrise with the moon horizon. So now we use the curve of the horizon, but we try to take these multispectral photos when we radar is captured. We have operators, which is we are developed technology for positioning system, so that when we are like some orbit around the moon in the future, we could locate the position of the satellites. We have some SEL mission used from XU University. This is for civil event rapture. We have magnetometer mission, so we have many magnetometers in the satellite. We try to measure the magnetic satellite. And we have SAP mission. So we have these two solar array towers deployed here in this photo. In this model, like this you can see here also. And the deployment mechanism uses this kind of shape memory alloy. So it doesn't have a spring. Instead, you have some special material that when you hit it, it goes to opens. Then also this one I'm working on at the moment is Vertex satellite. This is to try to catch this from the birth of the universe. We have this extragalactic background light. So basically, we have to have very precise pointing and point the satellites to some region of the sky, and we collect light and use the measurements. Then we work in partnership with the Japan Space Agency, this ISAS lab, and this KG University. Here I'm working more in this to like communication integration with the bus, because we need to download from Astro, which became our main radio, so I need to connect this sheet like internet. And we show that we can do 200 kilo bps down. And we are integrating with the payload this extern for up to 5 megabps higher, sorry, down from the images from this system. Then, yeah, as you saw, we can, when we do this partnership with people, there are many different objectives. So we can scale in cost and complexity. We can also choose the success criteria that matters these. So we have some simpler missions like a birds 1 to 5 that are more to train people. So the people are learning how to make satellites. But also we have these ones I show you that are more a little bit more complex, and they have commercial applications. So success criteria is hard, they want more requirements. And in terms of cost, yeah, we can scale from 1 euro up to something like 6 euro, like Kitsune. And this Vertex is very expensive because of the active control systems. We can depend on what kind of partnership it is. Here. And our philosophy is this lead satellite. So this is based on the Toyota production system. Some of you in engineering study this system. So basically, the idea is satellite. So Toyota production system satellites for cars, of course, that they manufacture. For us, it means this satellite holds a lot of importance. So it doesn't change previous ideas, but we accept some kind of value of satellite and subsystem. It's not something that must never. And we can talk about risks. So we can use cheaper cost components and do less testing. And then we can also reduce the cost. So the idea is that satellite price goes very cheap, so that we can launch a second generation later if something doesn't work well. So we learn and we do it. So this is like some kind of lead satellite idea. And the idea is to deliver value to the customer at the lowest cost and shortest possible time, minimizing waste. And interestingly, the satellite becomes small in this philosophy. This is not what you're trying to do. It's not the purpose, but the result. So if you try to do this, it ends up the satellite can get small. And you can also apply this philosophy for bigger satellites. It also works. And there are some CubeSats that do not apply this. This is what we are trying to do in our lab. And then we have this kind of life cycle. So we start the mission here, sorry, with the contract and kick off the mission definition. We do this system architecture definition. We do like breadboard models. We do engineering models, like model. Then we launch and we operate it. And we learn. And then from this one, we give it the next project. And start like this one. So part of this is testing. So we have test facilities inside QTech. Is something different about this university. So inside our laboratory, we have this center for nanosatellite testing. So we have like a vibration machine, we have adequate chamber, we have some kind of thermal vacuum, we have clean rooms for assembly of the satellites. Then we have some machines for thermostating without water. Also, we can do short tests and outgassing and other measurements. And yeah, this is the picture of where I work. This is the biggest building in the campus. Then also 30 meters away from me, there is a smaller building. So this is LACW. Yeah. And inside LACW, we have this electric chamber of the ground station. We have thermal vacuum chambers, vibration machines, clean rooms, and we also have now altitude control facilities. So we have this sun simulator, and we have like health volts cage, and we have like this air guarding table, and we can test like up to 3 in this one. Now we are making a bigger one for 6. So after going through all of this process, the questions we ask ourselves in the laboratory is how can we start future satellite projects and pass on the technology? And how can QTech and LACW create some sustainable space programs to make a value continuous? So one of the answers to this question is that some kind of open source project that we share the information. We have this open source activity, but it's not just about software, it also includes open hardware. So we have this material. So whenever some birds program is finishing their activities, we collect all the information that was generated, such as like technical drawings, source code, PCB design, test procedure, assembly procedure, part list, test reports, some ICDs, and we make some text about the satellites, and we share this information with you. So this is, you can go to our GitHub, this website. It's called Birds Open Source, and yeah, here you can find some information, and you are guided to all these insights you were looking for. And the idea is for this open source activity, we want to collaborate. Mainly. So we try to maintain the bus. We try to help countries to make their first satellites. We try to advance the space, science, and technology, and involve the environment to the space sector. So at the moment, we have like 5 Japanese users, so external to QTech that are using our bus. And internationally, we have 4 countries that are using first space. There's some distribution. And these are the banks, right? So we make the open source activities to let the users work on satellite by themselves, so they don't depend directly on us. And we want to people to use our bus to accommodate do the accommodation for different mission payloads. We want people to check which cost components we have with flight heritage, so they can, if they have no idea what to select, at least they can start. We like to interact and give, so people can interact with us, give feedback, and contribute to things that end up going back to the birds project. So the birds bus can then grow up through the consortium activities. Then now is the final session of my presentation. I'm going to talk about the JQ program. So this is for people that have their universities and they have already some satellite or they want to make a new satellite and they are looking for some launch opportunity and capacity building. So JQ is a collaboration between JAXA, the Japan Space Agency, and the UNICEF Japan. And their idea is to make this collaboration between emerging space stations to get their first CubeSat, but you see first is cross because it's acceptable that it's not really the first. It's better deployed into lower orbit via the ISS, International Space Station. So this is the deployer that is on the International Space Station. It's called the JSOT. So yeah, your satellite goes with rockets to the International Space Station. Then after some days, it is released from there. And so the orbit is very similar to ISS orbit. Then maybe some of you are familiar with the KivoCube. So I know that someone we did application for this. I was helping at the time. And so KivoCube is different than JCube. So KivoCube is all about a zero cost opportunity for emerging nations, while the JCube requires it's a low cost, so there is some transfer of money. So the idea is that it's much easier to get this kind of program and have some cheaper launch opportunity. So what is the difference? So the launch price of JCube, yeah, is not free, but much lower than the market price. Then in the case of KivoCube, it's free. But on the other hand, you can launch larger satellites in this JCube program. And when you do the selection, it's easier to get approved. The committee reviews, and in this one is like only one selected, so very different. And then this is a big difference that when you make your satellite, you team up with a Japanese university and you do this capacity building. So people can go to Japan and learn how we do satellites there, and then they can come back and develop the capacity for the satellites in other countries. And the KivoCube is more just about capacity building, but there is not strong partnership. So yeah, if you want to know more about JCube, so JCube basically you are more likely to secure a launch slot than with KivoCube, and at a cost that is below commercial launches. So we have a record of collaboration with countries. So our foreign partners are here. So QTech is one of the universities that can be your partner in this JCube. And then we have already some satellites we have got between this kind of partnership. And we want to work with foreign partners. Well, it's our mission. I already told you it's to contribute to the diversity of the space sector. We want to assist newcomers coming to the space sector. But yeah, not all Japanese universities have this mission. So this JCube program, we will try to match it with the best university support, not only QTech. The typical flow is this one. If you go through the process, you need to make some contacts. So contact is something we are doing here, like I'm talking with you. So if you are going to do this JCube application, we have to leave, like we do this kind of remote or solutions. Then we do this exchange of email. Then we do something called statement of work, where we clearly separate what we do, what we do. Then we sign the contract. And for this one, we do some support, deal support. Then there is money transfer to Japan. And then actual work starts. So students can go to Japan, and they can do this kind of as full-time graduate students or research visiting students with the hands-on work and their own capacity doing. And then we launch satellite and we can operate the satellite. And then we start discussing what we do next. So the important points about this is, in-person meetings are important. So we should do this kind of conference, also this conference. Since I came here, you can use it to discuss these things. Then we need to have clear definition of responsibilities. If we do this kind of thing, we need to be careful about money transfers. This takes a long time. There are many dramas about this one. And the important thing is that we should not think about only one satellite, but in some continuous part. Yes. And what do we want as a university? Yes, just learning. So what we want is like more students, we want more papers because we want to do research. And we want to like improve our collaboration with international partners. And yeah, we also want to lower our launch costs because if we collaborate with some external university, our launch costs also reduce. Then these are the suggested schemes for collaboration in this JQ program, which is one of them is more about student exchange. So the students, both Japanese and non-Japanese students, they learn how to work with people from different cultural backgrounds. And another good scheme is that satellite is built outside of Japan, for example, but students come to Japan for studying and learning how to do some things. And they can use our facilities for testing, for example, in actual, so if they do something they cannot do in their campus, they can do that. And there's some, yeah, partnership. And the other idea is satellite is built in Japan, that people go in there to do it. So it can also be done. But the important point is student exchange. So it is better if the students are like going there and having like studying and learning how to make sure something like that because this makes everything better. So for this type of longer project, it's better if the students take more than 1 year, at least 1 year. And yeah, full-time graduate students are an option. And yeah, there are some rules. You have to pass secondary exam, and you have to follow the timeline of Japan, which is a big difference. You have to take care of all the time to send the students. But yeah, and some last things to talk about is that money transfer is necessary. So there is contract, so you have to take care of you have to ask for assistance for the legal section of your organization. And yeah, these are contract points, so you cannot use for the directory of stores. You have to answer the applications, and you have to compare with export control, which parts are moving. There is of payment deadline and so on. And there is this. So yeah, this is a summary of my presentation. So we do the Amazon training and capacity feedback. So you are interested in this opportunity. Another thing is that we can experience a very diverse environment, people from all around the world. Maybe only the United Nations have more diversity. It's a lot of diversity. And then, yeah, we want to do international collaboration. We do already, so we're going to expand this one. We want to allow you to use our test facilities for satellites over 30 kilograms. We want more people to become professionals of space engineering and also learn things about project management and system engineering skills to build the projects. So project-based learning. And finally, yeah, you can become professional space. That's it. Sorry if I pass a little bit of time. So yeah, this is my contact information. You can also scan this QR code if you create some contact in your phone. Yeah, I have some special thanks to these people that like students can say Rodrigo and I feel like PR team because they want to look at some materials that are
The payload exchange between projects, I'm not sure how it works.
In this one, for example, we did very precise pointing to because for some time we need to point to a specific region and collect the wire. When we are buying like S, so we just buy in that case because we don't have super good technology that we can say we don't need any help from ourselves. But on the other hand, something like low Earth satellite is mostly built by the students. So also purchase satellites. So that means for example, AOCS unit we use in this one, yeah, is mostly in-house. So you buy some components, but the algorithm and everything. So yeah, depends on the satellite and the condition. We have, depending on the budget, also we can choose to buy some things. So most of the time we are buying transceivers, and but other parts we are making in our like the bus system, VTH, APS, Yeah, when the students here ask, we still about opportunity like this.
On this experience with me. And like the fact like when you say yes, is you create you know, progressively. You answer that, and you know, start to move, and doing something demonstration and going by steps. So it's in this area of going fast, but sometimes going intensively, but it's slowly but surely it's inclusive. Anyway, if I was very interested, one question about the example of knowledge. Yes, from the project one. This one. You said you were a shareholder document for non-project knowledge. This project mission, you may see each one so how do you share these lessons from
Okay, so there are many someone we do right. So I would want to focus on this what I present was I work for first. So yeah, every problem we have in one satellite goes to the next one. So even though they look very different, for example, this is the 6U and it's a 3U. Yeah, we developed new software for the computer here and we're using this one. So and then we observe some phenomena. So for example, there was some noise but we're receiving because some things are expressed as latency. And this was generating some fake commercial the debug line was still so it's kind of thing that we've passed to the next line project. We keep a list of like the things we observe during the operation. It's nice that before some issue that we have. And yeah, even though it's not the same name or something or the same shape, this is like for me it was kind of like the first generation. Actually, Bird's true will be the first generation to be second. Then this cartridge will be the third generation. Also, one character environment is also third generation. Then the little part, then the markets are like fourth generation for us because we are really passing the knowledge. But it's not only documentation, but also because the people involved are the same. So they also like try to keep working. It's great. Yeah, the idea is that yeah, whenever we find some problems, yeah, we learn and then we discuss.
I think this lesson learned iteration is also extremely valuable.
Yes.
So,
Thank you. Thank you.
Muito bom, mas são muito interessantes, não é muito simples. Como é que eu mando meus alunos? Sorry. Sorry. So it's late. Very simple question. How do I send my students to the space in the international course?
Sorry, sorry, can you repeat?
How do I send my students to study there in this international course?
Okay, so
Can you use as a contact? No, you don't want that.
so there are many ways. So SCIC, right? So
SCIC, yes.
So,
This one.
PNST criteria because this is program from UNOSA in the United Nations, right? So they consider like that a country is under development. The criteria is that it has its own launch capability of satellites. So then for Brazil, it's still possible to get PNST funding, but it's much harder than for other nations. So this is what still is kind of one option, but you know, like with all the advances in Brazil, we are almost going out of the definition. Then another option is we support people to get scholarships from here, for example.
Movimento de compra. Aquele movimento can use your compra.
Yeah, I would forward the video to other people, but yeah, I can use the directly.
You will get something better for your honest.
No,
You will get some stuff. Thanks.
I will get the paper publication. That's what I want. So if we collaborate, then we publish something. Yeah, so my contact team wasn't the last slide. I also distributed the cards.
Yeah, I got your cards.
So it's okay.
Thank
And the main guy is this guy who said he is in charge of his fund. So I will direct you to him. Basically, he's the one who will design.
Any more questions? Well, Professor Eduardo is right. Do you have questions?
No.
No?
I can present privately to you.
Well, if you do not have any more questions, we are 5 minutes late, but I think everything is fine. Thank you very much, Victor.
Well, good question. I was very happy that people were interested. Yeah, and if you have any question I could not answer now, like later. Thank you.
Thank you. We are now going to the next section. Eduardo, do you want to know? Oh, okay. So I'm with you. Well, we are going for the last section. Just a second, while we take the technical setup.
So I promise it will be the last time you see me. So we are in session 7, and the name is Systems Engineering and Reliability Improvement. And so the presenter can start.
So here we have a little summary of how the presentation will go. Firstly, I'm going to talk very briefly about the PDQ-SAT project. Then I'm going to enter Alice's part of the article, which is management theory. And lastly, my part, which is information traceability. This paper is like the combination of mine's and Alice's undergraduate thesis. So it's a lot of ground to cover, and I'm going to try to be really straightforward. So if you have any questions, you can ask later at the end of the presentation. So the PDQ-SAT project, as we have already said in other presentations, is a project that intends to test electronic components in space environment. And this is being made by in UFMG with the collaboration of professors and students from several areas of the university. And we currently have 12 undergraduate theses that have been written since the start of the project. So we have a lot of material and a lot of data on the project since it started. And this is really where the main motivator of our work, of Alice's part and my part in this work, is to construct a robust and reliable management method to handle all of these aspects, all of these uh, data that we have scattered across the works and the requirements, for example. We have more than 100 requirements mapped already, and the solution is divided into 8 subsystems. Some of them were covered in previous presentations, like the EPS subsystem, which is one of the 6 platform subsystems, and the 2 payloads are a lithium sulfur battery and a supercapacitor that must be characterized in space environment. Here we have the list of the subsystem. I'm not going to explain them, so it's just to show their names, show the accounting. And we have, as I already said, 6 platform subsystems and 2 payload subsystems. And as I said, the battery and the supercapacitor. So regarding the management theory part, basically the work was to search these 3 different areas and create a management method that was suitable for our approach, which is a university project that involves students and professors, and we must ensure that it is multi-generational, that it covers a lot of generations of students and researchers and professors. And for that, the project management sector, the mainly reference that we used was the PMBOK guide, which is a well-known reference in this field. For the space systems engineering, the NASA Systems Engineering Handbook was the main focus, main reference it utilized. And for the space systems project management, as a recommendation of our sponsors, or sponsor, the Space Brazilian Agency, we use the ECSS norms. I will cover them really quick right now. So the PMBOK guide was used mainly for the general management good practices. So like it divides its content into process groups and knowledge areas. And I'm gonna show, so at the end, all the documents were made, and the PMBOK was used for the most general part of management. But the ECSS standards were used for the space segment part, so they have more an approach that is more focused on space projects. And I'm going to show it right here. They have the focus is most on the project phases. They divide the project into phases and reviews for the project to occur. And here we have the documents that were created by Alice. Their names is that identification code on the left, which is PDQ as for PDQ SAT, and for management, and the number of the ID of the document. So like the visual standardization is PDQ-M00, is the first document that was created, and it's just a visual standard for the other documents. The project charter is the first document, and we have all of the other nine documents listed here in the respective areas. So like we can see that three of the documents are mainly focused on the PMBOK section, and that means they are more like general management good practices. So like the project charter, which is the opening document, and the closure document are more focused in the PMBOK section of this slide. As for the ECSS part, we have mostly the review. So like we must see if the project is ready for development, if it is ready for construction, if it is ready for flight, for launch. And this is most focused on the space project, so it makes sense that it is related with the ECSS norms. The ones in the middle, these three in the middle, are a junction of the concepts of both of the reference that were used. At the end, I'm gonna show how some of the documents turned out, but here is just a overview of this process that Alice used it to create the documents. And the objective is to be a simple but effective management method. So for my part, the graph theory and traceability, I'm going to start by defining what are graphs and what is traceability. Graphs are these structures that are shown in the figure below, which are basically vertices connected by edges. And why is this interesting for representing any kind of problem? Because it retains spatial information about the problem. So like if I have two items connected by a edge, it means that they share some kind of characteristic, they share some relationship between them. And so these kind of structures are used in different fields, such as social sciences, biological sciences, computer science, and is a very useful representation of problems that is used as I said in many fields. And traceability from the ENCODE definition is a association or relationship between two or more entities. So we can see the overlap of the concepts that I'm presenting here. Graphs show information connected by the edges, and traceability involves the connection between two or more entities. So what if we use graphs as a tool for traceability in projects, especially in space projects? This is the main focus of my part on this project, and I'm going to show you the results briefly. So for traceability, we have mainly three types. We have horizontal, which covers entities of the same type, vertical, which covers entities of different types, and bidirectional, which means I can go back and forth around the item. So I can go from item A to item B and go back from B to A. This is extremely important, and we are covering it with our solution. So our solution is a tool called Obsidian. I don't know if you guys know it. It's a software that works around Markdown files, and it is used for note taking and productivity. And it enables cross references about notes created within the software. So like if I create a note like this example, and I name it note 1 and write inside it, this is note 1, it references note 2 and has the tag color red. You can see that note 2 is highlighted in blue because I made it a clickable item. So when I click it, I can go to note 2 that is also represented right here. And in the graph view of the software, there is made a visual connection to show the connection between the nodes. So the graph shows the connection between nodes 1 and node 2, as we see here. And another advantage of the tool is that we have really no limit of what we can do with it. We have no limit of what you can write in the notes. We can create tags for it. So like here I create a tag named color and a sub tag named red and another named blue. So just we could color the notes and filter them if we like. So for the part of the tags, here are all the tags that I created for the project. We're mainly tracing requirements, needs, subsystems, team members, stakeholders, and documents. So for the requirement part, you can see that the major part of the tags is around the requirement segment. We have like functional or non-functional requirements. We have different levels of criticality and different levels of the requirements as well. We can go for like a high level of abstraction for mission level requirements to a down level for component requirements. And these colors can be used for viewing, for customization, but also for filtering the graph. And I'm going to show you the result really quick. Here's our approach to connect the different kinds of information, which is basically like a stakeholder that generates a requirement associated with a subsystem and managed by a team member. So you can see down here in the image how the connections are made. We connect all of these 5 types of information with this kind of logic that I told you right now. And in the requirement node that I opened here in the software, we can see how it connects to the other nodes. Like the need node is connected in origin field. So like this requirement was originated by this need node. And if I click the need node, I go to its content. And it's going to be a lot more clear when I show it functioning and at the end of the presentation. So like this is our complete graph right now. We have, as I said, more than 100 requirements, 79 needs, 39 team members mapped, 16 stakeholders, and 11 documents. These 11 documents are the documents that Alice created in her undergraduate thesis. And so here are just two examples of filtering that we can do. We can filter the graph to show only the subsystem and the requirements that have the subsystem level requirements. Or at the right, we can show only the subsystems and the functional requirements. And now I'm gonna switch to the tool right here, right now, just to show you guys. Let me see if yes, you can see this. That's nice. So here we have the graph that I just shown you. And basically, you can see that it has a lot of information to cover here. And I'm going to just show you how basically how it works. So like you have all the nodes, the tags in the right, and our files in the left side of the tool. And I've set some predefined views of the graph. So like I can show only the requirements divided by the level. If I click here, we show that the colors have changed, and we have filtered to show only the requirements and color them by level. So like we have the 4 levels that I mentioned earlier that are mission level, system level, subsystem level, and component level. And if like I go back to the standard view and click one of the nodes, let's see like the battery one. We can click it and we can see that it makes a table. It's made through a JavaScript code. It makes a table with all the requirements that reference this node, this subsystem. So like we can see that it has 11 subsystem, 11 requirements that connected to this subsystem, which are dedicated exclusively to this subsystem. And there are 2 other requirements that are shared with other subsystems. So if we like hover above this requirement, RNF 46, we can see that it mentions both the supercapacitor and the battery. And we can see that its origin is the need in SPC4. We can hover over it and see its content as well. It came from the stakeholder, which is the chemistry department at the university. We can go there and see that we have more content to show. And it has also a table that lists all the needs that came from the stakeholder. So we can see a lot of useful information on this. The documents that Alice created are here as well. I can open them really quick just to show you. We have like the opening chart is in this note. I can attach PDF files from it. I see that 3 requirements reference this document. And if I open the PDF, you can see how the documents turn out to be. So this is the first document that is created besides the Visual Standards, and it's the project charter, which is basically a opening to the project. And she created these documents, mainly the last ones, in order for us to fill it while the project will go on. So like the mission review, preliminary review, critical review, flight review, all will be fulfilled when the time comes for doing it. So I think that's it. I'm gonna open now for questions so I don't pass so much the time that I have to present to you. I'm gonna leave the graph right here, but if you want to go back to the presentation, you can tell me any moment.
I'm sure some.
I'm listening to you guys right now. Now I can listen. Can you hear me?
Yeah, are you still hear us?
Now I can. I can hear you.
Okay, so we were uploading and thanking you for your presentation, so thank you.
Thank you.
Already. And then we were, maybe a question, but I saw a question.
So in practice, how is the collaboration around this kind of technology like Obsidian? Do you feel like a group of many people they can log in some documents faster and smoothly? How is you on yourself when you start interacting with other people?
I don't know if I understand you really well, but you asked how the Obsidian tool is useful for the project. Is that it?
Yes. How is the interaction between the users of this one?
Oh,
So,
okay,
the people that are not you are gonna use this one. Then how do they feel like and how is the experience?
Perfect. This graph in Obsidian was a creation of mine, so like I'm very familiar with it already, but the other members may not be familiar with it like I am. So like, as for the moment, the two main people that use this tool is me and Professor Maria Cecilia. So there are other members of the project that we are including in the usage of Obsidian because it's a new approach that we are developing. And for the sharing of the files for the tool, we just instruct people to download the tool, which is really easy, and we share the files with them so they can open the tool and open this directory of information and navigate around it. So like we have a viewing mode that does not allow us to write anything. We can see that if I click here, I enter the writing mode. So there is no fear of people like mistyping anything or anything like that. And another tool that I am using we are studying the possibility to use it with the project is GitHub. So we can use GitHub to host the information on the graph, and so people can make updates, maybe make different branches of information. And I hope I answered your question.
Yes, I will so perfect. Thank you.
Thank you.
Yeah, thanks very much. Any other question? So I just had one, I think, quickly. It was, so you haven't used yet this tool on the project, you just started using it, right? But I think it would be very interesting to have the feedback when you are using it, to know how this can help. Because of course, different tools are great, but then it's, when it's really useful, then
Only have requirements, needs, and subsystem maps and stakeholders. So after some time, Professor Maria Cecilia asked me, what if we included team members on the graph as well, which are these pink notes right here, these pink notes. Let me highlight them really quick. These ones. And I started including them, and in each note we have contact info about each member. So like if I hover someone right here, like Israel, we have phone number, email, so we can contact them. And these kinds of facilitating mechanisms are helping us a lot to develop the project. We are mapping requirements directly on the tool and mapping relevant information directly on the tool, and we are organizing everything here, like the thesis from the students are here as well. So it's been really good to use this tool for the project.
okay. Thank you very much for maybe another round of applause.
Thank you.
Now we will move to the next presentation. So the title is Systems Engineering of a Brazilian Amazon Imaging CubeSat Constellation with Fritz Sat.
So, hello everyone, my name is Luis. I'm a currently engineering student at the University of Cincinnati. The food science. So, so the idea of this project is to apply engineering and the mission definition of a constellation concept for environmental monitoring of the Brazilian landscape. So the work objective is to define the steps in which engineering to define the mission, the objectives, the requirements, and the principal systems composed of the application. First, we have the scenario analysis, in which we analyze the current systems we use for the monitoring and the challenges they face. So we decided to go with these three main topics: the forestation monitoring, the fire monitoring, and the hydrologic monitoring. Here we have the stakeholders analysis, which is the next step. And the stakeholder analysis as the stakeholders, the contributions that stakeholders have, and the personal goals of each one. So in here we have the company in which they're going to contract Lucy with the goal to profit from the data collected, and the UFSC with the goal of space research is going to create the mission and the space and ground systems to collect this data, so the company can sell this data to the final user to use in agriculture and research, and infrastructure and logistics, and other stakeholders in this big picture is INPI, which is going to be used in two different ways: through leash, through validation and testing of the satellites, and through the INPI ground station in Natal. And the other stakeholder we have is the Brazilian government, and the goal is to the development of the national knowledge. And we are searching for proposals, causal proposals. So the goals and objectives of this work: the first goal is to obtain critical data to monitor the Brazilian Amazon. The second goal is to create legacy documentation so we can develop a methodology for adapting the systems engineering for the who is currently being used in satellites, and to adapt it to using nanosatellite projects. And the goal is to develop nanosatellite imaging technology in Brazil. So after that, we have the feasibility analysis of this space mission. And with that, we analyze different approaches we could follow through with the mission. And each approach has its own advantages and disadvantages. So we analyze each one and are going to present what. So the first idea will be the utilization of existing systems, which have the advantage of the systems is already in operation, so the development and operation costs are significantly lower, but it also comes with compromises and emission since the operation is already in motion. The next approach is the combination of the existing newly development systems. And the advantages of that are also the costs and the reliability of already existing parts, while incorporating new technologies in the existing system. And the disadvantages of that is that it requires careful coordination and ensure it needs a lot of coordination to ensure the compatibility of this data between all these different systems. The third one is through a large satellite, which offers the extensive data acquisition and processing capabilities, but it also comes with high costs and development time, and all of that. And last but not least, we have the constellation of nanosatellites, which presents a more flexible solution, a more cost-effective solution, and can provide a broader coverage of the area. It requires also a lot of coordination to make all of these nanosatellites to work together and to integrate this data. So after analyzing all of the important metrics for our projects, we went with the cost efficiency and the data autonomy metrics, which we use to analyze all the approaches. And then we decided that the best support is with the constellation of nanosatellites. So since we have the possibility of making a constellation, we also thought that we could divide the payload used. So through the three topics we had, which are the fire monitoring, the hydrological monitoring, and the deforestation, we could separate those payloads and make the different emissions. About that later. After that, we did the analysis of the interfaces. So we have two major interfaces, which are the first one is the satellite with the monitoring scenario, which is the data collection. And the other one is through space systems and ground system, focusing the telecommunication, telemetry, and the data that is going to be sent to the ground station. So the next step on this engineering is the concept of operations. So in here we have the constellation concept of operations. So there is the collection of the data. So each satellite would collect the data independently. Then we have the scheduling. So the ground station will determine which satellite is going to collect the data at which time. Then there's the transmission, and each satellite is going to send this data to the ground station independently. And there's the integration, when in the ground station is going to process all this data and together for the overall data. So here's the first mission that we decided. The name is EVI, and it's used for deforestation activities. And its main data collection sensor is through a multispectral camera. The other one is ICA2, which monitors the hydrological variables, and the data collection is through a SAR sensor. And the third one is TATA, which is to detect monitor fires, and it uses a thermal sensor as the data collection. So in the end, we have the general concept of operations also, which is the whole life cycle of the constellation. So there is the conception with the initial assessment, the scenario analysis. There is the design, which we are doing right now. It's the payload selection in system interface. And after that, we have the manufacturing, the construction of the satellites in and of itself, the launch of said satellites, the commissioning, which is the post-launch testing and calibration. And there's the operation of the satellites, in which they're going to collect the data. And after that, the decommissioning and disposal of the satellites. So in conclusion, this approach gave us a significant contribution to addressing critical points of the environmental issue. And the insights made from this work will help us to move further and develop everything. So, team, and I'd like to thank you all for listening. We'll also be glad to answer any questions.
One of the engineers in UP as well, he recently created a startup with other engineers, and we're doing research with sugar canes in São Paulo, and actually sold their company for some millions to the Serasa industry. And it was a idea very similar to that. They were collecting data from sugarcane plantations, and I just wanted to tell you about it because it's a very similar work, and it's great that you guys are doing that with the Amazon forest.
Thank you. I didn't know about that. Look more into it.
Okay, any other question? In the room? No? Well, I had one question, and I didn't understand exactly what was driving the reason to have a constellation. Because you showed some criteria, and then you went, okay, we need a constellation, but didn't understand why.
Yeah, analyzing all the approaches, we came across some metrics that we could use to define what was the best approach for us. And the idea of the project we did few matrices and all that to analyze, and we went with the most cost efficient and the better data autonomy. With those metrics, the constellation of nanosatellites was the best option to analyze the metrics.
And so you included the cost of launch, of having many.
Yes, yes,
okay.
All this because of the operation.
Okay. Okay. Any other question? Otherwise, we can thank the speaker. Thank you very much.
with plantations and give data from this plantation, like humidity or other data, for us here in Spapec. Here we have a brief agenda of our presentation, and for our satellite, we are developing it with the Federal University of Santa Federal University of Santa Catarina. Our satellite is a heritage from Floripasat-1, which was a satellite developed by them a few years ago. And most of the parts are similar to them, but because we are developing it here for the first time, we are trying to have a lot of information from them. The main focus of our paper is the battery case. One of the key components of our satellite is the battery management board. And during launch, we have a lot of problems with losing of the batteries. So we, in this paper, are trying to understand and to project the battery case to improve, to reduce the risk of losing the batteries during the launch. Here, just as any satellite, when as I explained, the launch can cause losing from the vibration of the rocket. And for that reason, we are trying to analyze it by peer analysis. Here we have an example of validation that we can do for the vibration analysis with a shaker. We are planning to buy one here for SunEsmatec, not only for the aerospace analysis, but for oil and gas applications too. Here is the object of study of our paper. The main idea is that the battery case is a key component, but when we analyzed the Floripasat-1 battery case, we understood that the battery case was a little bit bulkier, and we could reduce a little bit of weight in this structure. This is the final geometry that we are planning to fabricate in the next few months, but for this paper, we analyzed a little simpler one and tried to comply with CDS 14 for the analysis. For all projects that we developed here in SunEsmatec, we go from a concept study, material definitions, modeling, validation by simulation, which our paper stops. But for our project here, we are doing them manufacturing stage. In here we can see the differences between the first concept 1, which was developed by Floripasat, the concept 2, which is the concept that we evaluated in the fair analysis, and concept 3, which was the result from our fair analysis. And this one is going to be used in our satellite. Just for a brief explanation from our simulations analysis, we started with a static analysis in which we evaluated the assembly loads. The main idea is that when we pre-stress the battery case, it reflects how the modal analysis work and affects the natural frequencies and shape modes. With the modal analysis, we can find the participation factor and the effective mass, which are the main variables for us to understand in which directions we have to improve the structure of the battery case and increase its rigidity. After the modal analysis, we can do a random vibration analysis based on the graph 14, which we can understand how the structure responds for a sample of random variation that may occur during launch. Here, some simplifications and assumptions we did for the numerical model. The main idea is that we started with a linear elastic model with small deformations. Even though the contacts between PCB and the bolts are frictionless, and the contact between the PCB and case are frictionless, because in the final satellite, when it goes to launch, all the parts are glued with resin. We use the contact bonded, which the idea is that it keeps all things together and the whole body vibrates as one, even though they are different materials. Here we have a list of our materials used in the analysis, and it's important to mention the properties of two materials. The PCB, which was one of the materials with higher stresses in our analysis, and also PQ, which was the material used in the battery case. In here, for this static analysis, we used tightening load for the bolts with 350 newtons in the first step. And after the assembly, we evaluated the acceleration of the rocket with HG acceleration. We also fixed the battery case, the PCB in its assembling rows in all the degrees of freedom. After that, we go for the model analysis and for the random variation analysis. In the random variation analysis, we use this table here in the top right to evaluate the effect as a load for the analysis. In the bottom right table, we can see the mesh parameters used in the analysis. In here, our first results. For the static analysis, as you can see in the image in the top right left, the higher stress found were 253. But this only occurred in the PCB. For the battery case, which are the key component that we are evaluating in this paper, the stress found were very lower, in the magnitude of 10 to 20 MPa. And because of that, the safe factor in the static analysis is around 1.7. As I mentioned before, we use the participation factor and the effective mass to understand which directions of the case need increasing rigidity. So when we multiply these two factors that are given by the model analysis, we can find the critical modes. And for this instance, the mode 1, which has a natural frequency of 990 Hertz, has the need to increase the rigidity, not only in the X rotational direction, but also in the Y rotation direction. The idea here, when we see the vibration in this mode, the structure tends to open and close like this, but also present a rotation in the other axis. And because of that, we did that other design, increasing the rigidity in the other directions. For the random vibration analysis, the top line here is the input of load that I showed in the table. And in here, we can see the output of the analysis with a measuring point inside of one of the batteries. This is important because we can see if the structure is reducing or amplifying the vibration that we put in the analysis. And as we can see, it was reduced by a lot. But for the Z direction, which is the direction that we consider the launch, it was higher, the vibration, the green line. And also we can see the effect of the natural frequency that we need to improve for the geometry that we show here, with a peak around 10 to the times 3. For the conclusions, we understand that our structure can withstand the launch efforts, but we needed to change its geometry. Here we have an example that we printed here at LACW, but we are planning to do use another manufacturing process because this is a FDM process, and we intend to use a pounder-based technique. And here we have an image of our satellite from the time we did the paper for today. We started with manufacturing, and we are also intending to change the way we are fixing the structure, the PCBs in the structure. We saw a lot of problems with assembly that we are currently working to solve right now. This is our references, and I open to questions.
Yes.
First, congrats on your project. It's amazing. I wanted to know what were the main difficulties that you guys had in this project, and also what you think is it will be the next steps to make this case even better and even more lighter and more useful for your next projects.
Well, the first one is that we are, this team is very new for us. I am an automotive engineer, and our team has no aerospace engineers. So we have the best this year, we had to grow a lot in knowledge to understand the aerospace ambient and to know where we are going to. And not only the mechanical parts that we already have some experience, for the electronic parts that is not my area, but I think is the most difficult part for us as per right now.
So one more question. From the vibration perspective of view, you guys already made some analysis with ANSYS, and including that you guys are going to also test in bench, probably in each with some chain whatever. What do you guys pretend doing with the data collected in the test and comparing it with the data with the analysis? Do you guys have some aims, some goals for this comparison?
First, we try to destroy the prototype because we want to see how much vibration can handle. Of course, because it's our first project in this field, we are looking forward to validate it. But I think because of the partnership with LACW 1 and your team, probably we are going the right step. And these modifications are only to get a lighter structure, not for change the whole design. That's why we kept the concept of the battery case also.
Nice. I just want to say one more thing. I'm really
Last.
So I can talk to you later.
No, but you can ask me.
I actually was going to thank you and all your team because that project actually what we did first like one, and I built it. And now for me, seeing you guys doing the research in this project and making it even better and better, for me, it's I can only ever be happy about it because seeing that we can exchange studies and research between all these institutions around here, UFSC, Sinotec, UFSC Joinville, also WebMT. For me, it only brings me joy. So thank you for you and everyone in your team.
Thank you as well. Thank you.
Okay, any other questions? Those will be. It was a very good point. Last. Thank you again to the presenter. Now, it's the presentation. And to design of a low-cost solar simulator for CubeSats. CubeSats.
Ainda tipo o show do milhão, né? Era aquele que ele filme, né? Né? Ele não lembra, não, cara. Muito parecido, cara. E ele tem um jeito assim, né, de se comunicar bem, né?
My name is Maria. Graduation first engineering mechanic in UFSC, the University of Pennsylvania. And today I'm going to present the work of the design of our course simulator courses. Just a second. Just a second. Okay. We just had a little technical problem. Don't worry.
So how do you feel to be the last presenter of this session?
Yeah, it's telling that it's, I think it's here in Brazil, we're saying like to close with a golden key, like. Yeah.
We finish the conteúdo.
Yeah.
Esse aqui é o último. Foi esse aqui. Foi esse aqui, isso a gente apresentou. Esse aqui que a gente passou por isso, foi apresentado. Negócio aqui. Tem que fechar fechar é quando fechar. Ah, liga embaixo. Vai caber, não. Isso, tá ligado. Pronto, pode ir. Obrigado, pode falar. Agora, isso, pode ir. Vai falar. Vai bater, é bateria. Isso, isso.
Yeah. Okay. Okay, so I'm going to start right now. So I'm just like that. So the next point. Okay. So here is our agenda for today. And to start, let's talk about CubeSat a little bit. So the CubeSats are low cost, and they have the objective to make this more easy for the research go to space. So we have to think about it that the main point of CubeSats are in the academic fields, and it's a place where we don't have so much money to produce CubeSats and to do all the research we want to do. So we have to make different tests and different ways to do all we want to do. One of the problems of the CubeSat is the electrical power system that is really sensitive, and it's really crucial for the mission. So it's really important for us to test. And here is a photo of the Floripasat 1, and let's go for the next. And so the objective of this project is to develop a low-cost solar simulator for CubeSats and test energy generation and the power management of the systems. So we are thinking about it and developing equipment to test the panel solars and the batteries at the CubeSats. And for that, we want to simulate to mimic the orbit. So when we have a satellite in orbit, we have the points where here we have like a lot of sunlight for the panels. Here we have just a little bit, and here we don't have enough. Where's the eclipse? And we want to test all of this in a easy way, so we can have a low cost, because of a point. The three parts we want to test is the energy harvesting unity of the solar panels, and we want to test energy storage unity, the batteries, and we want to test the power distribution unit to the proper flow at the CubeSat, so we don't have the problem at the energy in the CubeSat. And for that, we think about it, a box. We have to put some lights then inside it, and simulate the orbit there with the light of the lamps. So here are the box. We thought about it, these proper dispositions with coolers. Here, I don't know if you can see it because it's really small, but here's a LED, the coolers, and the CubeSat inside it. We made at this point the box like this way because we study about different projects about it, and we have a lot of sun simulators, but not so much low cost sun simulators. And for that, for these projects, as I said, we want to simulate, we want to do it with a 2-unit CubeSat. So we have placed it like the wants to fit the 2-unit CubeSat inside of the box. So the key components, I said, is the lights that simulate the light, the cooling systems for not to burn, we don't want that, and the CubeSat inside it with a support, so the panel solars can have a uniform light at it. So now the main components. We thought about a box made of MDF because it's a low-cost material, and studying of the thermal conditions, the MDF was the proper one and the better one to design to deal with. And the LEDs were there here, and the heat sink. But the structure, so I said it, it's big. Here we have the dimensions to can fit a 2-unit scope set inside. So more of the structure inside it, we have 10 LEDs with this exactly properties because of the simulated solar irradiance. We have like 1,000 watts per square meters that we have to take of the irradiance at the LEDs to simulate the sun. So to do that, we have to have 10 high power LEDs. And for not to burn again, it's really important. We take cooler systems that we have coolers and heat sinks, and it's a commercial one, so it's easy to find. It's one that I think is having inside of our notebooks and stuff like that. So it's easy and low cost too. So here you can see the lab. And here we have the structure to support the 2-unit scope set. And for that, is for the panel solars can have the incidence of the light of the lamp. This part is made of, we think about the PLA. We have like all these projects where they use PLA for to all the box, but we don't think it's a good idea because of this parameters. So WaveJF is better, but just for the support, it's a good idea because it's better to for the production. We can do it at the lab with a machine, a 3D printer. So, and now the applications and benefits. So, for that, why this is so important? Why this is so cool? Like make a sun simulator at the lab, because we can test experimentally our panel systems and the APS at your level at your lab. So you can test and see if you're gonna have problems before the missions. Because when the CubeSat is on orbit, we all know that we can do it with so much stuff about it, and then we can test before. And we can have improvements, so in the performance. So if you see not a problem, but something you can do better, you can test before. And we can reduce the missions risk. I had a presentation on Professor Ederman that I said how important is the EPS and how the batteries can be the most effective part of the missions risk or the failure of the project. So this is other benefit. And here is the project, all the projects. Here is the bar, and we have support inside it, the LEDs and the heat sink. And it's a really low cost sun simulator, and it's a easy one. We have a lot of ideas to improve the solar system. So we want to fabricate a driver to control this LED and make sure they are having the right light for simulate all the orbit points. And I think it's that. Thank you. If you have a question.
I'm the organization of work. I would like to ask if you plan to make a turntable to put the satellite so you can control the movement of the angle.
No, we are just thinking about it to control the LED. So a part of the box, like I don't know, maybe this part it's light on, this is not, and maybe we can control with the Professor Edelman. They have like the professor do it a job about it. He had us at the orbit, so he has the data, and he helps me with this work. And was about it to make this code that he has and put in the drivers to control the LED and not to make the table to turn. But it's a good idea. It's really a good idea. I don't think about it yet.
Other question? Yes.
So you're using LEDs to simulate the sunlight. Maybe it's something, they have like a black body temperature is like 6,500, so it's close to the sun. Okay, but they measure on what's the emission spectrum. Does it match more or less the sun?
Yeah.
How can you do this approximation?
Yeah, it's like we have these parameters that is approximation of the sun here.
Yes, exactly.
So the temperature, yeah, and then have it's like this. This is the most hard things to do because of to not have we don't have a problem with the thermal parts. Like we don't have so much heat that we can like touch the box. That is the top problem. We can put a lot of flats, but if you can control the heat, gonna like have a big problem to take out the cassette side.
Okay, but so you need so you need it's 1,000 watt per meter.
Yeah.
6,700.
Yeah.
Other question?
No.
Just a special pose. Any other question? Okay. I had one question, at least one. So one point is about Paulo was saying was for standard irradiation, there is a specific spectrum match to be able to assess the proper efficiency of the solar cell, and also phase or something. So it would be good let that you choose to compare it with the actual spectrum to see if it mimics really the sun or not, because then you have different efficiency first. Then I'm not convinced about using the MDF, and if it's super cheap. It's nice for a prototype, but you have a lot of electronics and wires and so on. If you have a spark, it will burn. So you are creating a hazard. So maybe, investing a little bit more, then MDF can be something better. And
we are just the next step is to do simulations for make sure that MDF is the proper one. Because I don't feel like that is a good idea too, but it's the better one that we yeah, and for making this comparison of some scale and some data. But we want to do a simulation.
And I have some other issues with, that's quite good, interesting to have 4 lights. Normally, when you have a cell simulator, you have only one light that is a bit far, so you have you can expose the whole solar cell. So I don't know here if you're exposing the whole solar cell, because the LED seems quite small. I don't know how. Anyway, if you reduce the light just to simulate that you're turning, then you're not able to see any issues because of shadowing or maybe efficiency due to angle on the solar panel. So I'm not an expert, it's just a feeling. So think about that, because maybe it's better to have one big one and then be able to turn, because then you will really mimic all the shadowing. If you have an antenna or whatever things sticking out, it will shadow, so it will reduce the projection of the light. And that would be mimicking a bit better. Some food for thought. Okay, thank you very much. We can approach again. round of applause for sticking until the end of today. So thank you to all of you. So we will, yes. So how do we do? Will everyone go out? Yeah, everyone goes out? Just us. Just us. We go out. So we if they go out, they're out. Yeah, okay, okay. So if we go out.